Every ancient monument began with a decision. Someone chose that exact location. Someone believed the project was worth years, sometimes decades of labour. Someone convinced thousands of people to shape mountains, transport stone, or build cities where none had existed before. Those decisions once made perfect sense to the people who lived there. Today, many of them seem almost impossible to understand. We can calculate the size of the structures, identify the materials, and estimate their age with remarkable accuracy. But the thinking that gave birth to them has largely vanished. Across the ancient world, the greatest mysteries are often not hidden inside the stones themselves, but inside the minds of the people who placed them there, and that is a mystery no excavation can uncover completely. The slope of Mount Mithridat in Kerch, Crimea, hosted an ancient city built where flatland barely existed. That city was Pantikapaeum, the Greek capital of the Bosporan Kingdom, rising above the Kerch Strait like a stone machine designed to control sea, grain, and power. Its ruins were not discovered in one dramatic moment. They were slowly uncovered through excavations on Mount Mithridat, where walls, foundations, tombs, coins, ceramics, and public buildings revealed a city founded by Milesian Greeks in the late 7th or early 6th century BC. Ancient sources and archaeology show that Pantikapaeum became one of the most important Greek settlements on the northern Black Sea, eventually covering about 100 hectares at its peak. But the greatest mystery of Pantikapaeum is not simply that it was large, it is how it stood. The city was not placed on an easy coastal plain. It climbed a hill. Streets, houses, temples, workshops, defensive lines, and elite buildings had to be fixed onto an unstable slope. To make this possible, ancient engineers created a stepped urban landscape using massive terrace and retaining walls. These walls were not decorative. They were the hidden skeleton of the city. Without them, Pantikapaeum would have slid down the mountain. A retaining wall is one of the most unforgiving structures in engineering. A normal wall only carries its own weight and the load above it. A retaining wall must fight the earth itself. Behind it, soil pushes sideways. After rain, water gathers in the ground and increases pressure. If drainage is poor, the force can multiply until the wall cracks, bulges, or collapses. Modern engineers calculate this with soil mechanics, hydrostatic pressure, safety factors, and laboratory tests. The builders of Pantikapaeum had none of that language, yet they produced a terrace city that survived for more than 2,000 years in fragments. This is why the retaining walls are so mysterious. They suggest not a single building trick, but an entire lost system of practical geotechnical knowledge. The builders had to understand which parts of Mount Mithridat were solid enough for foundations, where the slope needed cutting, where fill could be added, and how much mass was needed to hold each platform in place. They also had to predict what would happen decades later, after storms, frost, earthquakes, repairs, and the weight of new buildings. A terrace wall that works for one small house may fail when a temple, public hall, or stone road is added above it. Pantikapaeum was expanded over centuries, so each generation inherited the risks created by the last. The archaeological remains show that the city's acropolis occupied the summit and upper slopes, while later districts spread downward. This means the urban plan depended on artificial levels. A terrace is not just a flat surface, it is a negotiation between gravity and architecture. To create one, workers cut into the hill, built a stone face, filled the space behind it, compacted the fill, and then placed buildings on top. If the fill settled unevenly, walls above would crack. If rainwater could not escape, pressure would build behind the stonework. If the wall was too thin, the entire platform could rotate outward. The unanswered question is how the builders judged these risks. Greek cities had experience with fortifications and stepped sanctuaries. But Panticapaeum was different because the terrain was not only sacred or defensive, it was urban. People lived, stored goods, moved animals, traded grain, and built workshops on these levels. The walls had to function every day, not just impress the eye. This kind of engineering is usually invisible when it succeeds. The city looked like architecture, but underneath it was controlled earth pressure. The scale makes the problem larger. Panticapaeum's maximum area is often given as about 100 hectares, a vast size for a Black Sea Greek city. Even if only a portion of that occupied the steepest slope, the volume of stone, rubble, clay and labour required was enormous. A limestone block weighing 1 or 2 tons is already difficult to move on level ground. On Mount Mithridat, every block had to be brought upward, positioned against gravity and locked into a structural sequence. The builders probably used sledges, rollers, ropes, wooden levers, ramps, and coordinated labour teams. Yet the exact construction method remains uncertain because the machines have vanished. The temporary ramps are gone, and the surviving walls show only the final result. There is another hidden problem: drainage. A retaining wall without drainage is a trap. Rain falls on the upper terraces, enters the soil and creates lateral water pressure. In winter, freezing can expand moisture inside cracks. Over centuries, this can destroy even thick masonry. The survival of major wall sections suggests that the builders may have used rubble packing, porous backfill, channels, gaps, or carefully selected stone layers to let water move away. But archaeology has not fully reconstructed the complete hydraulic logic of the terraces. We can see that the system worked well enough to preserve the urban form for centuries. We cannot yet see every decision behind it. This makes Panticapaeum comparable to other great ancient hillside cities, but with its own character. Pergamon in Asia Minor used monumental terraces to support royal buildings. Athens used retaining structures around the Acropolis. Roman towns later mastered vaulted substructures and concrete platforms. Panticapaeum belongs to an earlier and more hybrid world. Greek colonists, Scythian neighbours, Bosporan kings, Black Sea trade and local limestone technology. Its retaining walls were not built in a laboratory of pure Greek design. They were shaped by frontier conditions, local materials, and the pressure of a growing capital. The city's location explains why such effort was worth it. Panticapaeum stood near the Cimmerian Bosporus, the narrow waterway linking the Black Sea and the Sea of Azov. From this position it could control shipping, grain routes, fish resources, and access to the fertile steppe. By the 5th and 4th centuries BC, it became the political centre of the Bosporan kingdom, ruled first by the Achaean Actids and then by the Spartatid dynasty. Its coinage, including silver from the 5th century BC and later gold and bronze, shows a wealthy urban economy connected to the wider Greek world. But wealth alone does not build stability. The builders needed organisation. Quarrying stone, transporting it, preparing mortar or packing material, levelling terraces, maintaining roads, and repairing walls required administration. Panticapaeum was not just a city of merchants, it was a managed construction system. Every terrace implies surveyors. Every retaining wall implies labour planning. Every long-lived platform implies maintenance. The real mystery is not whether ancient people were capable. They clearly were. The mystery is how their technical decisions were recorded, taught, checked, and transmitted over generations without the manuals, instruments, and engineering formulas used today. The defensive story deepens this puzzle. Recent archaeological interpretation has connected destruction layers, collapsed wall remains, fire traces, and Scythian-type arrowheads with a violent disaster around 400–475 BC. If this interpretation is correct, early Panticapaeum faced attack and rapid fortification at a crucial stage of its development. That would mean some walls were not built slowly under peaceful conditions. They may have been raised under pressure, using limited time and available materials, yet the city did not disappear. It recovered, expanded, and eventually became the capital of a kingdom. This resilience suggests that Panticapaeum's builders could adapt their engineering to crisis as well as to long-term urban growth. The upper city also raises questions about water. A large settlement on a hill cannot survive on prestige alone. People need drinking water, washing water, workshop water, and emergency reserves. Wells, cisterns, rain collection, and possible channel systems would have been essential. But water management on a terrace slope is double-edged. The same water needed for life can destroy foundations if uncontrolled. The builders had to collect, store, redirect, and drain it. That balance between useful water and dangerous water is one of the most technically demanding parts of hillside urbanism. Then there is the port, much of which has vanished or remains difficult to reconstruct because coastlines change, sediments move, and later construction covers earlier remains. Panticapaeum's prosperity depended on maritime exchange. Grain from the northern Black Sea was valuable to Greek markets, especially Athens. A capital of this kind needed warehouses, docks, loading areas, roads from harbour to upper city, and systems for storing goods before shipment. This means the terraced hill and the harbour below were probably connected as one economic machine. Stone walls held the city in place above, ships moved wealth below. At the edge of the Don River Delta, near the Sea of Azov in southern Russia, stood a Greek city built farther into the steppe than almost any other. It was called Tanais. Founded between about 290 and 260 BC, Tanais stood at the meeting point of two worlds, the Greek trading cities of the Black Sea and the nomadic peoples of the Eurasian steppe. It was not a marble city like Athens, not a buried disaster like Pompeii, and not a monumental port like Alexandria. Its mystery is quieter. It lies in trade, storage, river mud, ceramic technology, and the strange survival of objects made to carry liquid across thousands of kilometers. The site was not discovered in one dramatic moment. Ancient writers such as Strabo mention Tanais, but the ruins near modern Nedvigovka were identified and excavated mainly through modern archaeology, with large-scale research continuing from the 20th century onward. Today only a fraction of the city has been uncovered, yet the finds already show a place that functioned for nearly 8 centuries as a frontier machine of commerce, diplomacy, and engineering. Tanais was built in a difficult landscape. The Don Delta was not solid stone. It was a changing zone of silt, clay, marshland, seasonal flooding, river branches, and shifting shorelines. For a city dependent on trade, this was both opportunity and danger. Too far from the water, and ships could not reach it. Too close, and floods or erosion could destroy it. Unlike Chersonesus in Crimea, which had access to firmer coastal terrain, Tanais had to survive on a river edge where the land itself was unstable. Yet its streets, houses, fortifications, and harbour-related structures suggest planning, measurement, and long-term adaptation. This is where the first technical puzzle appears. How did Greek builders choose a location that remained useful for trade for centuries in a delta landscape? Ancient surveyors had tools such as ropes, measuring rods, sighting instruments, and water levels, but they had no satellite maps, no sediment models, and no modern hydrology. Still, the city was positioned well enough to become one of the largest trade centres between Greeks and steppe nomads. UNESCO's description of the site calls Tanais the farthest northeastern extension of the Hellenic cultural sphere, and a major emporium between Greeks and nomads. Its walls tell another story. Tanais was damaged more than once, including the ravaging of the city by King Polemon at the end of the 1st century BC, and later destruction around the middle of the 3rd century AD. But after destruction, the city returned. Streets were rebuilt. Defensive lines were reused. The settlement did not simply vanish and restart as a random village. It retained a memory of layout. That implies preserved survey points, surviving foundations, or a practical building tradition passed from one generation to the next. In Pompeii, urban planning was frozen by volcanic ash in AD 79. In Tanais, the challenge was different. Planning had to survive violence, abandonment, rebuilding, and a moving river environment. The building materials add another layer. Tanais was not surrounded by endless high-quality building stone. Large stones, roof tiles, timber, clay, metal fittings, fuel, food, and water all had to move through a logistical network. Every wall block was not just a stone, it was evidence of transport. Every repaired tower meant quarrying, hauling, storage, and labor control. In a frontier city, this matters. A place like Alexandria could rely on imperial-scale infrastructure and Mediterranean shipping. Tanais operated at the border of the Greek world, where roads, rivers, carts, animals, and political agreements all had to work together. But the most revealing technology at Tanais may not be its walls, it is the amphora. At first glance, an amphora looks simple. A clay jar with 2 handles, a narrow neck, and a pointed or rounded base. But in the ancient world, amphorae were industrial containers. They were the shipping barrels, fuel tanks, wine bottles, oil drums, and customs labels of the Mediterranean and Black Sea economy. Thousands of fragments from sites like Tanais are not just broken pottery. They are data. Their clay fabric, shape, stamp, residue, and repair marks can reveal origin, contents, trade routes, taxation, and even preservation technology. Tanais received amphorae from across the Black Sea world. Sinope, Rhodes, Heraclea, Pontica, Chersonesus, and other production centres. Many carried wine, olive oil, fish products, or other liquid goods. Compared with inland settlements of the steppe, this is extraordinary. Amphorae were heavy, fragile, and expensive to transport. A large transport amphora could hold roughly 20 to 40 litres, depending on type, and when filled with wine or oil it could weigh more than 40 kilograms. Moving hundreds or thousands of them required ships, docks, storage yards, counting systems, and handlers who knew how to stack fragile containers without losing the cargo. The mystery is not whether Tanais traded. The mystery is how precisely that trade was controlled. Many amphorae were stamped before firing. These stamps could include names of officials, manufacturers, workshops, or production centres. In the Black Sea region, stamped amphora handles are one of the strongest pieces of evidence for commercial links, especially with places such as Sinope and Chersonesus. They worked almost like ancient tracking codes. A stamped handle could tell archaeologists where the container came from and sometimes narrow its date to a specific period. But this also means ancient merchants were not moving anonymous jars. They were moving standardized goods through a system that required trust, weight control, volume expectation, and legal recognition across cultures. Then comes the deeper technical question. How were these amphorae made reliable enough to preserve liquids over long journeys? Clay is porous. A fired ceramic vessel can still absorb liquid through microscopic pores unless the clay body is dense enough, the firing temperature high enough, or the interior is coated. Ancient amphora production required careful clay selection, levigation, temper control, wheel forming, drying, and firing. Typical ancient ceramic firing often reached roughly 800 to 1000 degrees Celsius, depending on kiln type, fuel, and atmosphere. Too low, and the vessel remained weak and porous. Too high, and the amphora could warp, crack, or vitrify unevenly. The potter had to control temperature without thermometers. That alone is impressive, but liquid storage demanded more. Many amphorae used organic linings, pine resin, pitch, wax, bitumen, oils, lime mixtures, or combinations that varied by region and cargo. Modern chemical studies of ancient amphorae use techniques such as gas chromatography, mass spectrometry, Fourier transform infrared spectroscopy, and Raman spectroscopy to detect residues invisible to the eye. These methods have identified pinaceae resins, heated pitch markers, fatty acids, oils, and other compounds in ancient ceramic containers. In simple terms, the jar was not just fired clay, it was a composite storage technology. This is where Tanais becomes fascinating. A frontier city receiving imported amphorae also received invisible chemical engineering. Wine shipped from the Aegean or southern Black Sea did not survive only because of the jar shape. It survived because the interior surface may have been sealed, disinfected, flavored, or protected by resinous coatings. Pine resin could reduce leakage and slow spoilage. Pitch could waterproof the ceramic. Wax could help seal stoppers. Bitumen could provide a strong barrier in some regions. Lime and oil mixtures could form water-resistant compounds. But the exact recipes were rarely written down, and organic materials decay, oxidize, or chemically transform over 2,000 years. So archaeologists face a paradox. The amphora survives, the technology inside it often does not. Imagine a ship arriving near Tanais with hundreds of amphorae. Each jar had to be formed to a recognizable standard, fired without fatal cracks, lined with a substance suitable for the cargo, sealed at the mouth, marked or stamped, loaded into a ship, cushioned by packing material, unloaded near the Don, stored through seasonal temperature changes, and then sold or redistributed to nomadic groups of the steppe. In winter, the region could freeze. In summer, heat could expand liquids and stress seals. A poor stopper could ruin wine. A porous wall could leak oil. A wrong resin could alter flavor. A weak jar could break during transport. This was not primitive trade. It was applied material science. The shape itself was engineering. Narrow necks reduced evaporation and made sealing easier. Handles allowed lifting, tying, and pouring. Pointed bases could be packed into ship holds using sand racks or layered cargo arrangements. Similar shapes across the Mediterranean were not artistic coincidence. They were solutions to repeated transport problems. A jar had to fit the human body, the ship's hold, the warehouse floor, and the merchant's accounting system. Yet at Tanais, the amphora raises questions that remain difficult to answer. Were empty jars reused locally? Were broken amphorae recycled into building material, drainage fill, or floor packing? Did merchants at Tanais refill imported containers with local products? Could steppe traders recognize stamps and trust them as quality marks? How much of the city's economy depended on amphora-based goods, rather than grain, hides, slaves, livestock, or metals? Archaeology can count fragments, classify forms, and analyze residues, but it cannot fully restore the daily intelligence behind the system. Even preservation itself is uncertain. When a residue test identifies resin, it does not always reveal the full recipe. Was the resin boiled once or repeatedly heated? Was it mixed with beeswax? Was the vessel warmed before coating? Was the lining brushed, poured, smoked, or rotated inside the jar? Did different cargoes require different coatings? Fish sauce, wine, and oil do not behave the same way. Garum-like fish products are salty, chemically aggressive, and strongly scented. Wine is acidic and sensitive to oxidation. Olive oil can become rancid. Each cargo demanded different protection. On the shores of the Black Sea, near modern Sevastopol in Crimea, stands an ancient city where stone ruins still preserve the blueprint of a complete Greek world. This was Chersonesus Taurica, a city founded by Dorian Greek colonists in the 5th century BC and later shaped by Roman and Byzantine power. Its ruins were systematically excavated from the 19th century, with major archaeological work beginning in 1827. What appeared at first to be another Greek colony soon became something far more unusual. Not only a city but a preserved agricultural machine with streets, walls, farms, vineyards, roads, towers, workshops and wine installations locked into one engineered landscape. Chersonesus is mysterious because it does not look like a random settlement that grew slowly without control. The city and its surrounding Kora were planned as one organism. UNESCO describes the site as an outstanding example of an ancient Greek polis and its agricultural territory, established mainly during the 4th and 3rd centuries BC. The protected World Heritage property includes the ancient city and several preserved plots of agricultural land, showing how urban life and rural production were connected over more than 2,000 years. From above, the mystery becomes clearer. The countryside around Chersonesus was divided into regular agricultural parcels by stone walls. Roads, field boundaries, farmsteads, defensive towers, and production areas were arranged with a level of order that feels almost modern. These were not decorative ruins, they were working infrastructure. The land was measured, divided, protected, cultivated, harvested, processed, stored, and connected to maritime trade. The first technical puzzle is surveying. Ancient Greek engineers had measuring ropes, sighting tools, and practical geometry, but the Kora of Chersonesus suggests a system that could control distance, angle, and boundary across a large landscape. In a normal field, a small error in measurement is harmless. Across an agricultural territory used for generations, small errors become roads that do not meet, walls that drift, drainage that fails, and land disputes that never end. Yet Chersonesus preserved a remarkably coherent rural grid. The second puzzle lies under the city itself. Streets, drains, wells, cisterns, and channels show that water was not treated as an afterthought. Chersonesus had no giant river flowing through it. Survival depended on collecting, moving, and protecting water in a coastal environment exposed to wind, salt, seasonal rain, and human waste. The engineering question is not simply how they built drains, but how they calculated slope, maintenance access, and long-term flow without modern instruments. A drain that is too flat clogs, a drain that is too steep erodes. A city that mismanages water collapses quietly. But the most powerful mystery is not the wall, the street, or the drain, it is wine. Chersonesus was not only drinking wine, it was producing it at scale. The surrounding Kora preserved vineyards and installations linked to wine pressing and storage. Archaeologists have found evidence of wine presses, wineries, and agricultural facilities across the territory, showing that viticulture was central to the city's economy. This changes the way we should look at the ruins. A wine press is not just a stone basin, it is a machine. Grapes must be harvested at the right time, transported before rot begins, crushed without wasting juice, filtered or settled, moved into containers, fermented, sealed, stored, taxed, and shipped. Every step requires control. If one link fails, the product spoils. Ancient Chersonesus seems to have solved this problem through landscape engineering. The vineyards were not isolated gardens, they were connected to a measured land system. Parcels made labor predictable, stone walls protected boundaries and possibly reduced erosion. Roads allowed carts to move grapes from field to press. Towers gave security in a frontier zone where Greek colonists lived near Taurian, Scythian, and later wider Black Sea powers. The result was not a romantic countryside. It was an industrial agricultural network. The presses themselves raised difficult questions. In many ancient wine installations, grapes were crushed on a raised treading floor, and juice flowed by gravity into a lower vat or collecting basin. That sounds simple until we imagine the required precision. The surface had to slope enough for liquid to move, but not so much that skin, stems, and sediment rushed into the wrong chamber. The collecting vat needed waterproof lining. The stone had to resist acidity. The edges had to prevent leakage. The whole installation had to be cleaned repeatedly, because uncontrolled bacteria could destroy the next batch. The ancient producers of Chersonesus did not have stainless steel tanks, chemical sanitizers, hydrometers, refrigeration, or laboratory yeast cultures. Yet they operated in a region where seasonal temperature could vary strongly and where fermentation is extremely sensitive. Too much heat can make wine harsh or spoil it. Too much oxygen can turn it sour. Dirty vessels can introduce unwanted microbes. Modern wineries spend enormous effort controlling exactly these problems. So how did Chersonesus manage consistency? Part of the answer may lie in empirical knowledge. Ancient winemakers knew from experience when grapes were sweet enough, when must was active, when sediment should settle, and when vessels should be sealed. They may have used resin, pitch, clay linings, or organic coatings to protect containers and reduce leakage. Amphorae were the shipping technology of the ancient Mediterranean and Black Sea world, and stamped handles are one of the key tools archaeologists use to trace production, chronology, and trade. But experience alone does not explain scale. A family can make wine by memory. A city-state producing for export needs standardization. Amphorae must hold roughly predictable volumes. Seals must survive transport. Workshops must produce containers fast enough for each harvest. Merchants need recognizable shapes and stamps. Officials need taxation and quality control. The wine economy of Chersonesus therefore implies not only farming skill, but an administrative system able to coordinate land, labor, ceramic production, storage, and maritime exchange. This is where the mystery becomes technical. We can see the final objects: presses, basins, field walls, amphora fragments, stamped handles. What we cannot fully reconstruct is the operating manual. How many workers handled one harvest? How were grapes sorted? Were different vineyard parcels assigned to different press houses? Did the city regulate amphora stamps as an official mark? How long did fermentation last in local climate conditions? Were wines separated by quality, age, or destination? The stones survive, but the process has vanished. Compared with Aegean wine centres such as Thasos or Chios, Chersonesus also sits at a sharper frontier. It was a Greek city on the northern Black Sea, facing steppe societies, changing trade routes, military pressure, and a harsher climate than many Mediterranean vineyards. Producing wine here required adaptation. The technology was not simply copied from Greece. It had to be adjusted to Crimean soil, rainfall, temperature, local stone, transport distances, and market demand. That adaptation may explain why the Cora matters so much. The city's true innovation was not one mysterious device. It was the integration of many ordinary technologies into one durable system. Surveying made the land legible. Walls made property stable. Roads made harvest movement possible. Presses turned grapes into liquid value. Amphorae turned liquid into trade goods. The harbour turned local production into Black Sea commerce. And still, several questions remain open. How did ancient surveyors maintain such regular land divisions over generations? How did farmers prevent soil exhaustion while keeping vineyards productive? How are wine installations cleaned and maintained? How did they control fermentation without modern temperature control? How much wine could the city produce in a good year? And how much of the economy depended on this one fragile liquid? Tucked away on a limestone hill overlooking the fertile plains of southern Spain, Torre Paradens appears at first glance to be just another forgotten Roman ruin. Yet beneath its weathered stones lies one of the Iberian Peninsula's most intriguing engineering puzzles. Excavations carried out since the late 20th century have revealed a city occupied from around the 6th century BC until the early Middle Ages, preserving massive Iberian fortifications, a Roman forum, temples, baths, and one of the best preserved monumental gates in Hispania. Located roughly 50 kilometers southeast of Cordoba, the settlement covers nearly 10 hectares. But what truly astonishes archaeologists is not its size, it is the remarkable technical knowledge hidden within a city built on one of the most difficult landscapes imaginable. The discovery of Torreperda's unfolded gradually rather than through a spectacular accident. Local farmers had long known of scattered carved stones protruding from the fields, but systematic archaeological surveys during the 1980s and 1990s revealed that the hill concealed an entire urban centre buried beneath centuries of soil. Excavations uncovered an Iberian oppidum that later evolved into a Roman municipium known as *Itusi Virtus Iulia*. Remote sensing, aerial photography, geophysical surveys and careful stratigraphic excavation have since exposed only a fraction of the ancient city, suggesting that much of its infrastructure still lies hidden underground. Every new excavation season raises more questions than answers. Perhaps the greatest mystery begins with the hill itself. Torreperda's occupies a limestone plateau rising approximately 579 meters above sea level. Unlike the broad plains where Roman colonies were often established, this summit is uneven, fractured by natural joints and interrupted by steep slopes. Constructing an organized city here would have required extensive modification of the landscape long before the first temple or public building could rise. Modern civil engineers typically rely on excavators, laser levels, GPS surveying, and reinforced retaining structures when preparing similarly difficult terrain. Ancient builders possessed none of these technologies, yet the streets, public squares, defensive walls, and ceremonial buildings align with surprising regularity. Some exposed bedrock surfaces appear intentionally flattened, while others seem carved directly into the limestone itself. Archaeologists can observe the finished result but still struggle to reconstruct the sequence of engineering decisions that transformed an irregular hilltop into a stable urban platform. The city walls deepen the mystery even further. Stretching for nearly 2 kilometers around the settlement, the Iberian fortifications remain among the most impressive defensive works in inland Andalusia. Several surviving sections exceed 2 meters in thickness and were constructed from enormous limestone blocks, many weighing several tons each. Unlike the precisely polygonal masonry of sites such as Sacsayhuaman in Peru, Torreperda employs roughly squared blocks, carefully arranged to distribute weight across the hillside. The engineering challenge was not merely cutting stone. Every block first had to be quarried, shaped, transported uphill, positioned accurately, and integrated into walls capable of resisting both gravity and military attack. Experimental archaeology suggests that moving a single 3-ton block using wooden sledges may require 40 to 60 workers on level ground. Moving hundreds of such stones uphill across rocky terrain would have multiplied the logistical complexity dramatically. Yet no dedicated transport roads, lifting machinery, or large quarry staging areas have been conclusively identified. The physical evidence demonstrates that the work was accomplished, but the practical methods remain largely invisible. One feature illustrates the builder's sophistication particularly well: the eastern monumental gate. Rather than creating a simple opening through the walls, the designers produced a carefully engineered defensive entrance incorporating multiple layers of protection. The passage narrows approaching the gateway, forcing visitors into a confined corridor where defenders positioned above could control movement. Thick parallel walls distribute structural loads away from the opening, reducing the risk of collapse while simultaneously strengthening the weakest point in the fortification. Similar defensive principles later appeared in Roman military architecture and even medieval castles across Europe. Whether Roman engineers borrowed local ideas or independently refined comparable solutions remains debated. But the Tauroparodon's gateway demonstrates that Iberian military engineering had already achieved an impressive level of structural understanding centuries before the Roman conquest. The foundation beneath these massive walls presents another unresolved question. Limestone bedrock is both strong and unpredictable. Although capable of supporting tremendous loads, it naturally develops fractures through weathering and groundwater erosion. Modern engineers perform extensive geological investigations before placing heavy structures on fractured rock. Ancient builders possessed no drilling rigs or computer models, yet the surviving walls display remarkably little long-term settlement despite enduring over 2,000 years of seasonal temperature fluctuations, earthquakes, and erosion. Southern Spain experiences moderate seismic activity associated with the complex interaction between the African and Eurasian tectonic plates. Even relatively small earthquakes repeated over centuries gradually weaken poorly designed masonry. Tauroparodon's has survived them all. Whether the builders intentionally selected the most stable rock, reinforced natural fissures with hidden techniques, or simply benefited from extraordinary empirical knowledge remains uncertain. Water management introduces another layer of engineering mystery. Building a city atop a hill solves many defensive problems but creates severe hydraulic ones. Every rainfall threatens erosion, while every dry season demands reliable water storage. Archaeologists have identified channels, drains, and carefully sloped streets directing runoff away from important buildings. The gradients appear subtle but deliberate, indicating careful planning rather than accidental adaptation. Similar hydraulic precision can be observed in Roman cities such as Pompeii, where street slopes averaged only a few degrees yet effectively controlled stormwater. At Tauroparodon's, however, much of the drainage network remains buried. Geophysical surveys hint at additional underground structures whose exact functions have yet to be confirmed. The visible channels may therefore represent only a small portion of a far larger hydraulic system still concealed beneath the surface. Even more intriguing is the city's sanctuary dedicated to healing. Hundreds of small limestone votive sculptures representing eyes, legs, arms, internal organs, and entire human figures have been recovered from the sacred precinct. Such offerings suggest pilgrims visited the sanctuary seeking cures for illness, much like worshippers at the great healing sanctuary of Epidaurus in Greece. But healing centers require one essential resource: water. Springs, ritual fountains, baths, or purification basins formed integral parts of many ancient medical sanctuaries. Tauroparodon's, however, occupies a dry limestone summit where natural water sources are limited. No definitive hydraulic installation capable of supplying large numbers of pilgrims has yet been identified. Rainwater harvesting through underground cisterns remains the leading hypothesis, yet the storage capacity currently documented appears insufficient for centuries of continuous religious activity. Somewhere beneath the unexcavated city may lie reservoirs or conduits that have not yet been discovered. The urban plan itself raises equally fascinating questions. Excavated sectors reveal an organized network connecting the forum, temple, market spaces, residential districts, and public buildings through relatively regular streets. Such order might seem unsurprising for a Roman town, but evidence indicates that many spatial decisions originated during the earlier Iberian occupation. Roman administrators often imposed standardized planning based on orthogonal street grids, yet at Tauroparodons they adapted substantial portions of the pre-existing settlement rather than rebuilding from scratch. That decision may reveal an uncomfortable truth. The indigenous engineering they encountered was already highly effective. Similar respect for earlier urban infrastructure occurred at only a limited number of conquered settlements across the Western Mediterranean. Located in modern-day Jublains in northwestern France, the massive Roman fortress appears at first glance to be just another late imperial military installation. Yet, from the moment archaeologists began systematically excavating the site in the 19th century, they encountered a paradox. The walls were among the strongest ever built in Roman Gaul, but almost everything inside suggested that the structure was never intended to function as an ordinary fortress. More than a century of excavations, aerial photography, laser scanning, geophysical surveys, and architectural analysis have revealed a monument that continues to challenge historians. Nearly 17 centuries after its construction, the greatest mystery is no longer who built it. It is why Roman engineers devoted such extraordinary resources to a building whose true purpose remains uncertain. The fortress was erected around the late 3rd or early 4th century AD, during one of the Roman Empire's most unstable periods. Germanic incursions threatened the Rhine frontier, civil wars erupted between rival emperors, and provinces throughout Gaul strengthened their defences. Yet Jublains stood roughly 500 kilometres from the nearest frontier. Unlike famous military centres such as Hadrian's Wall or the Rhine forts, it lay deep inside territory that had been securely Roman for nearly 3 centuries. Archaeological surveys have uncovered no evidence of a major siege, no widespread destruction layer, and no battlefield surrounding the complex. Nevertheless, Roman authorities invested an astonishing amount of labour into constructing one of the strongest fortifications in Western Gaul. The outer walls reached nearly 4 meters in thickness, reinforced by massive corner towers and carefully engineered gateways. Such dimensions rival defensive works built in regions facing constant military danger, raising an obvious question. Why build a fortress capable of resisting a major assault where almost no enemy army was expected to arrive? The mystery becomes even deeper after crossing the walls. A normal Roman castellum followed a highly standardized layout developed over centuries of military experience. Archaeologists would expect to find long barracks capable of housing hundreds of soldiers, granaries elevated above damp ground, workshops, kitchens, wells, stables, administrative headquarters, and large open courtyards for training. Instead, Jublains offers surprisingly little of this. Excavations revealed relatively few internal buildings, almost no evidence for a permanent garrison of significant size, and remarkably limited traces of prolonged military occupation. The enormous defensive shell encloses an interior that appears strangely empty. It's almost as if Roman engineers concentrated their greatest efforts on protecting something that has since disappeared, rather than on accommodating troops. Some researchers have compared this contradiction to constructing a modern nuclear bunker with almost no living quarters inside. The architecture simply does not match its apparent function. One increasingly discussed hypothesis suggests that the fortress protected not soldiers, but wealth. During the Roman period, Jublains served as the capital of the Diablintes, an important administrative district complete with temples, baths, a theatre capable of seating several thousand spectators, forums, and government offices. Tax revenues, official archives, military payrolls, or imperial supplies may have been stored here, Such facilities would have required exceptional protection without necessarily housing a large army. Comparable secure storage complexes existed elsewhere in the Empire, although few matched Ublain's in defensive sophistication. Yet this theory introduces another puzzle. Despite decades of excavation, archaeologists have discovered no treasury, no large concentrations of coins, no archive rooms, and no secure vaults that definitively explain the fortress's immense defensive capability. If valuable materials were indeed stored here, they vanished almost completely before history recorded their fate. Equally impressive is the engineering itself. Modern laser surveys demonstrate that many surviving walls remain remarkably straight despite standing for nearly 1,700 years. Some sections still rise over 8 meters high, while their vertical deviation measures only a few centimeters. Such precision required extraordinary control over foundation preparation, stone cutting, and load distribution. Roman engineers achieved this without steel reinforcement, powered cranes, hydraulic concrete pumps, or modern surveying instruments. Instead, they relied upon simple devices including plumb lines, measuring rods, the groma for establishing straight alignments, and the chorobates for leveling. Compared with modern construction tolerances, maintaining structural stability over walls nearly 4 meters thick across centuries of weather, freeze-thaw cycles, and ground movement represents an astonishing engineering achievement. The mortar itself continues to attract scientific attention. Like many monumental Roman buildings, the fortress employed opus caementicium *, the famous Roman concrete composed of lime, volcanic or local aggregates, crushed stone, and carefully graded filler materials. Electron microscopy and mineralogical analyses of Roman concretes elsewhere have revealed complex chemical reactions producing durable calcium-aluminum silicate hydrates that continue strengthening long after construction. While Ublain's did not benefit from the volcanic ash available around the Bay of Naples, its builders adapted regional materials to create a remarkably resilient structure. The precise recipes remain uncertain because subtle variations in lime quality, aggregate size, water content, mixing sequence, and curing conditions dramatically influence long-term durability. Modern laboratories can reproduce individual ingredients, yet reproducing the overall performance of Roman structural concrete consistently remains an active field of materials science. Even more mysterious is what lies beneath the visible walls. Geotechnical investigations indicate that the fortress rests upon foundations showing remarkably little differential settlement, despite centuries of environmental change. Modern structural engineers understand that uneven settlement represents one of the greatest threats to heavy masonry buildings. A difference of only a few centimeters between foundation points can generate cracks propagating through entire walls. Yet Ublain's displays relatively limited structural distortion considering its age and mass. Roman builders clearly understood how to distribute loads across local geology, even though no surviving engineering manuals describe exactly how they evaluated subsurface conditions before construction. The knowledge almost certainly combined practical experience, empirical observation, and generations of accumulated craftsmanship that disappeared with the collapse of Roman administration in Western Europe. The entrance system reveals another layer of sophisticated military thinking. Rather than allowing attackers to approach directly, the gateways forced anyone entering to change direction repeatedly while exposing vulnerable sides to defenders positioned above. Modern computer reconstructions demonstrate that these controlled movement corridors dramatically reduce the momentum of any assault force. Similar defensive geometry later appeared in many medieval castles, yet Ublain's predates most of them by centuries. The striking question is why such advanced defensive planning was applied to a location that may never have experienced a major attack. Was the fortress designed according to standardized imperial regulations, regardless of local threat? Or were Roman engineers anticipating dangers that never materialized? The logistics required to construct the complex are almost as extraordinary as the finished building. Estimates based on wall volume suggest that tens of thousands of tons of stone had to be quarried, transported, shaped, lifted, and positioned with remarkable precision. Every cubic meter of masonry required additional lime production, itself demanding enormous quantities of firewood. Experimental archaeology indicates that producing 1 ton of quicklime can consume several tons of limestone together with substantial fuel, creating an immense supply chain extending far beyond the construction site. Roads had to remain functional, wagons maintained, animals fed, workers organized, and materials stored in carefully coordinated sequences. Without centralized administration capable of managing labor, taxation, and transportation, such a project would have been nearly impossible. Glanum, hidden at the foot of the Alpilles near Saint-Rémy-de-Provence in southern France, was not built around a palace, a fortress, or a gold mine. It was built around water. For centuries, only the Great Roman Arch and the Mausoleum of the Julie stood above ground, known locally as Les Antiques. The city itself remained buried beneath fields and olive groves until systematic excavations began in 1921. What emerged was not one city but several civilizations layered on top of each other. A Celto-Ligurian sanctuary, a Greek-influenced town, and finally a Roman city folded into the stone valley. The strange heart of Glanum was its sacred spring. Long before Rome arrived, the local Salians seemed to have understood that this narrow limestone valley held something rare, a stable source of water in a dry Mediterranean landscape. Around the 6th century BC, they settled near the spring and dedicated it to Glanis, a healing water deity. Later, the Romans did not erase this cult. They absorbed it, connecting Glanis with Valetudo, the goddess of health. That alone makes Glanum different from many Roman towns. It was not simply urban planning imposed on conquered land. It was a medical, religious, and hydraulic landscape rebuilt again and again around the same source. The mystery is not that ancient people believed water could heal. Many cultures did. The mystery is how carefully Glanum appears to have managed that water. The spring was not left as a natural pool. It was enclosed, monumentalized, directed, and connected to basins, drains, baths, and sacred spaces. In Roman Bath in England, hot mineral water was held in a reservoir and settling tank before entering the bathing complex. At Glanum, the system was smaller and colder, but the idea is comparable. Sacred water had to be controlled before it could become ritual technology. The site sits on limestone terrain, where water moves unpredictably through cracks, cavities, and underground channels. That is the first technical problem. A spring in such a place can be generous, but unstable. Seasonal rain, underground pressure, mineral deposits, and sediment can all change flow over time, yet Glanum survived through multiple building phases. The same sacred source remained central from the Iron Age into the Roman period. This suggests that the builders did more than decorate a spring. They learned how to protect it. The most fascinating question is whether Glanum had an ancient form of mineral water treatment. Not treatment in the modern chemical sense, but a practical system for separating, cooling, settling, channeling, and preserving water, believed to have therapeutic power. Pilgrims did not come only to drink. They came to bathe, make offerings, and possibly sleep or pray near the sanctuary. For this to work, the water had to remain clean enough, visible enough, and controlled enough to maintain trust. A sacred spring that becomes muddy, stagnant, or contaminated loses its authority. This is where the archaeology becomes strange. The sacred basin and related structures show that water was staged. It was not merely collected, it was presented. Stone channels, basins, and drainage features imply an engineered path from natural emergence to human use. In a normal domestic system, water simply needs to arrive. In a healing sanctuary, water needs to appear pure, continuous, and almost supernatural. That means the architecture was doing psychological work as much as hydraulic work. Compared with large Roman aqueduct cities, Glanum was modest. It did not have the scale of Nimes, where the Pont du Gard carried water across 50 kilometers of terrain. It did not have the vast bath complexes of Rome, where thousands could bathe daily. But that makes Glanum more mysterious, not less. In a smaller town, every hydraulic decision mattered. A spring sanctuary, baths, houses, streets, and drains all had to coexist in a confined valley. Water was limited, yet it had religious value, practical value, and medical value at the same time. The Romans were famous for water engineering, but Glanum shows something older and more layered. The Gallic sanctuary came first. Greek influence then introduced more urban planning, courtyards, public spaces, and stone architecture. Rome later added forums, temples, baths, and monumental symbols of power. Each culture inherited the same water source and reinterpreted it. The unresolved question is how much of the original local water knowledge survived beneath the Roman rebuild. Did Roman engineers discover the spring and redesign everything from scratch? Or did they rely on knowledge already preserved by local priests, builders, and healers? The healing water technology becomes even more intriguing when we consider minerals. Groundwater moving through limestone commonly carries calcium carbonate and other dissolved minerals. Such water can leave crusts, deposits, and changes in taste. Ancient people would not describe this with chemistry, but they could observe effects: clear water, unusual flavor, skin sensation, deposits on stone, or perceived relief after a bathing. Over generations, repeated human experience could become a technical tradition. The builders may not have known molecular chemistry, but they knew which source was trusted, which basin stayed cleaner, and which flow should not be disturbed. This is not fantasy. Ancient medical cultures often linked water, minerals, temperature, and healing. Greek sanctuaries of Asclepius combined ritual with observation. Roman bathing culture combined hygiene, social life, and bodily treatment. Glanum seems to sit between these worlds. Not a huge spa city, but a local healing centre, where sacred identity and hydraulic design were inseparable. The Temple of Valetudo, dated to the late 1st century BC and associated with health, shows that Rome gave the spring a formal medical religious language. But the deeper cult of Glanis was older. There is another hidden technical challenge: contamination control. A healing spring visited by pilgrims, bathers, animals, vendors, and residents is vulnerable. Wastewater must be removed without polluting the source. Rainwater rushing from the Alpiles must be diverted. Sediment must be settled. Overflow must be carried away. The surviving drains and street gradients suggest that Glanum's builders understood the danger of uncontrolled water. In a narrow valley, a single storm could turn sacred water into floodwater. This is why the city's drainage system deserves more attention. The Alpiles are not high mountains, but Mediterranean storms can be violent. Dry channels can become sudden torrents. Building a sanctuary and town at the foot of such terrain meant facing periodic flash runoff. The streets, drains, and basins were not decorative. They were survival infrastructure. Modern visitors see ruins. Ancient engineers saw flow paths. The unanswered part is how they calculated it. Roman engineers had surveying tools such as the chorobates and groma, and they understood gradients extremely well. But Glanum's earliest water sanctuary predates full Roman control. If the original community already chose the safest position for the spring enclosure, then their environmental knowledge was remarkably precise. They may have mapped the valley not with instruments, but with generations of observation, where water rose, where it vanished, where floods cut the earth, where stone remained dry. The limestone foundation adds another puzzle. Karst landscapes can hide voids below the surface. Heavy masonry over unstable cavities can crack or settle. Yet Glanum's major structures, including the famous Mausoleum of the Uli, survived with exceptional preservation. The mausoleum rises about 17 meters and dates to the late 1st century BC, standing near the triumphal arch that marked the entrance zone of the Roman city. These monuments were not part of the spring system, yet they show the same broader technical confidence, building heavy stone architecture in a geologically complex valley. The city's cultural layers also create a mystery of continuity. Many conquered towns were rebuilt violently, their old sacred centers pushed aside. At Glanum, the sacred spring remained important. Rome did not simply replace the old god, it translated him. Glanis became compatible with Valetudo. A local healing cult became a Roman health sanctuary. This suggests that the spring had authority strong enough to survive political change. In practical terms, the water worked, or at least enough people believed it worked for centuries. Castro de São Lourenço was rediscovered on a granite hill above Villachar in Esposenda, northern Portugal, about 200 meters above the Atlantic coast. Serious archaeological work began in 1985, after modern disturbance exposed what had been hidden beneath the hill, an Iron Age fortified settlement later reused in the Roman period and again touched by medieval occupation. At first glance, Castro de São Lourenço does not look impossible. There are no giant monoliths, no pyramids, no carved statues staring across the centuries. What remains are stone walls, circular houses, paved spaces, defensive lines, and fragments of a vanished hilltop community. But the deeper question is not what they built. It is how they made a windy Atlantic hill function as a living machine for defense, housing, visibility, water, and survival for centuries. The site belongs to the wider Castro culture of northwest Iberia, a world of fortified hill settlements spread across northern Portugal and Galicia. These communities flourished before and during contact with Rome, and they often chose high places with strong visibility over valleys, rivers, coastlines, and routes of movement. Castro de São Lourenço fits that pattern perfectly. From its hill, the settlement could watch the coastline, the Cavado region, inland passages, and the surrounding landscape. In modern military terms, this was not just a village. It was a surveillance platform built into the terrain. Yet the strange part is the precision of that choice. The hill is not the highest mountain in the region, but it is high enough to dominate the coastal plain and close enough to the sea to control movement. This suggests a technical understanding of landscape that went beyond simple shelter. The builders were reading wind, slope, water, stone availability, enemy movement, and visibility at the same time. Today, archaeologists can model viewsheds with GIS software. The people of São Lourenço did it with observation, memory, and experience. The defensive system is one of the most important clues. The settlement was protected by 3 lines of walls, following the shape of the hill rather than forcing the hill into a geometric plan. This is very different from later Roman military camps, which often preferred straight lines, gates, axes, and rectangular organization. At São Lourenço, defense was organic. The walls curve with the land. The houses cluster around the elevations. The settlement does not fight the mountain, it uses it. That makes the engineering harder to explain. Building a wall on flat ground is one problem. Building a defensive system on an uneven granite hill exposed to Atlantic weather is another. The wall must resist gravity, rainwater, soil pressure, erosion, and centuries of seasonal movement. Even without mortar, the stones had to lock together with enough stability to survive. A badly chosen stone would create a weak point. A poor foundation would shift. A badly drained wall would slowly collapse from within. The fact that the remains are still readable after more than 2,000 years means the builders understood load, friction, slope and drainage in a practical way. This is where the dry stone construction becomes mysterious. Dry stone walls look simple because they contain no visible technology, but that simplicity is deceptive. In modern engineering, a dry stone wall survives through mass, interlocking geometry, drainage, and careful distribution of pressure. The stones must be selected not only by size, but by shape, surface contact, weight, and position. Unlike mortared masonry, dry stone construction must allow water to escape while preventing the structure from sliding apart. It is both rigid and flexible. It can absorb small movements without cracking like a solid cement wall. At Castro de São Lourenço, the builders had local granite, a hard and durable rock. But granite is not easy material. It is heavy, irregular, and difficult to shape with Iron Age tools. The real technology may not have been cutting perfect blocks. It may have been knowing how little shaping was necessary. Instead of forcing the stone into artificial precision, they turned natural irregularity into stability. In that sense, their method was almost the opposite of Roman ashlar masonry. Roman builders often displayed power through straight courses and standardized blocks. The Castro builders displayed intelligence through adaptation. The circular houses add another layer. Many structures were round or oval, a form common in Castro settlements. To modernize, a round house can seem primitive compared with a rectangular Roman building. But on a windy coastal hill, the round plan may have been an efficient solution. A circular wall has no exposed corner where wind pressure can concentrate. It also distributes roof loads evenly around the perimeter. If the roof was made of timber and thatch, the circular plan reduced structural weak points and allowed the building to resist storms better than a rectangular hut of similar materials. This matters because Castro de São Lourenço sits in an Atlantic environment. Wind, humidity, and rain are not background details. They're engineering forces. A house that works inland may fail on a coastal hill. A doorway placed in the wrong direction can turn a home into a wind tunnel. A roof with the wrong pitch can leak, rot, or lift under strong gusts. The repeated use of circular and oval forms suggests not random tradition, but long-term environmental testing. These were not drawings made in a classroom. They were solutions refined by survival. The spatial organization is equally interesting. Excavations revealed housing units, often with paved areas around them. That paving may look ordinary, but on a hill settlement it matters. Paved surfaces control mud, movement, drainage, and access between houses. They also prevent daily activity from destroying the ground around domestic structures. A settlement like this needed paths, working areas, storage spaces, and defensive circulation. Every stone floor was part of a larger system of movement. Compared with famous Celtic oppida in Central Europe, São Lourenço was smaller and more local in scale, but that does not make it less sophisticated. Large oppida such as Bibracte or Manching impress us with size, trade, and urban density. São Lourenço impresses in another way. It compresses survival into a difficult hilltop. Its technology was not monumental display. It was environmental control. It had to make a narrow, exposed, rocky place livable. Water is one of the unresolved questions. A hilltop settlement can defend itself, but it also creates a problem. Water must be collected, stored, carried, or controlled. People, animals, cooking, craft work, and daily cleaning all require a reliable supply. The more secure a settlement becomes, the more dangerous water shortage becomes during stress or conflict. At Saulenko, the full water management system is still not completely visible. Rainwater may have been collected, springs or lower sources may have been used, containers and storage strategies may have supported daily life. But the operational details are mostly gone. This is a recurring problem in ancient engineering. Stone walls survive, water systems often disappear, channels are destroyed, tanks collapse, organic containers vanish, and later occupation cuts through earlier layers. What remains is the paradox. The settlement could not have functioned without water management, yet the exact system is difficult to reconstruct. The absence of evidence is not evidence of simplicity. It may simply mean that the most important technology was fragile, reused, or erased. The Roman period complicates the story. After Rome expanded into northwest Iberia, many native settlements were abandoned, transformed, or absorbed into new systems. Castro de Saulenko was not simply erased. Its occupation continued into the Roman period, and the site shows different phases of use. That continuity is important. If the earlier layout had been useless, Roman influence might have replaced it more completely. Instead, the hill remained meaningful. The old defensive and domestic logic still had value. This creates one of the most interesting comparisons. Roman engineering is usually associated with roads, aqueducts, concrete baths, bridges, and standardized military planning. Castro engineering was different. It relied on local geology, inherited knowledge, and landscape intelligence. Rome could build across landscapes. The Castro people built with the landscape. At Saulenko, the meeting of these two traditions did not produce instant replacement. It produced adaptation. Deva Fortress rises above the city of Deva in Hunedoara County, western Romania, on Fortress Hill, a volcanic height overlooking the Mureș River Valley. The citadel is usually dated to the middle of the 13th century, with early references around Castrum Deva, and it was built on a hill recorded at about 371 to 378 meters high. Several local historical sources connect the hill with older Dacian occupation, while geological descriptions place its formation in Neogene volcanic activity, roughly 10 to 6 million years ago. That is the first strange fact. This was not a comfortable building site. It was a hard volcanic mass, steep, exposed, and difficult to supply. Yet medieval engineers turned it into one of Transylvania's strongest defensive points. The discovery of Deva Fortress is not the story of one archaeologist finding a lost ruin in the forest. It is the story of a fortress that never fully disappeared. It stood above Deva for centuries, visible from the town, damaged by war, repaired, abandoned, and restored again. Written sources mention the fortress from the 13th century, and later records show it changing function from military stronghold to noble residence and garrison. In 1453, John Hunyadi transformed it into a noble castle, strengthening its status in Transylvania. By the 15th to 17th centuries, many of the walls visible today had taken shape, including defensive chambers, gates, towers, and the central upper area. What makes Deva mysterious is not that nobody knows who built it. The mystery is technical. Why choose a volcanic hill so difficult to build on? Why force stone, lime, timber, water, weapons, food, and labor up a steep isolated height when easier locations existed nearby? The obvious answer is defense. From the summit, guards could observe the Mureș Valley, one of the important movement corridors of Transylvania. But defense alone does not explain the engineering. A fortress must not only see danger, it must survive weather, siege, fire, supply shortage, and the slow movement of unstable ground. The volcanic hill itself is the first hidden machine. Unlike soft earthworks, a volcanic neck gives strength, height, and visibility, but it also creates serious problems. Hard rock is difficult to cut. Irregular surfaces make foundations complicated. Natural fractures can guide water into walls. Steep slopes make collapse more dangerous. Medieval builders had no modern geotechnical survey, no laser scanning, no concrete anchors, no powered cranes. Yet the fortress was adapted to the rock instead of being forced into a perfect geometric plan. Its walls bend with the hill, its defensive belts follow the terrain, its gates and towers appear where the landscape allows control. This suggests a practical understanding of load, slope, and stone behavior that was never written down in a surviving engineering manual. The greatest unsolved question is logistics. A wall 2 meters thick is not only a wall, it is a supply chain frozen into stone. Every block had to be quarried, selected, carried, lifted, placed, and bound. Lime mortar required limestone or suitable raw material, fuel for burning, water for slaking, and skilled mixing. Timber was needed for scaffolding, gates, roofs, hoists, and temporary supports. Metal was needed for tools, hinges, weapons, and reinforcement. Even if some stone came directly from the hill, builders still had to shape it and move it across steep ground. If material came from below, then the problem became even greater. Today, visitors can climb by modern paths or cable car, but medieval workers had only animals, human carriers, sledges, ropes, and timber frames. The fortress seems to have solved this through phased construction rather than one impossible campaign. Deva was not built in a single moment. It changed across centuries. That makes the engineering more impressive, not less. Each generation had to attach new work to older work without destroying the stability of the hilltop. The visible remains include belts of fortified walls, gates, towers, the ruins of a palace and guard rooms. Such a layout required not only military thinking but long-term spatial planning. Builders had to know where pressure would move, where attackers would be slowed, where defenders could fire, where people could gather, and where supplies could be stored. Water may be the quietest and most dangerous mystery. A hill fortress without reliable water is only strong until thirst begins. Deva's summit has no easy river or spring like the valley below. A garrison needed drinking water, cooking water, water for animals, mortar preparation, cleaning, and fire control. In a siege, this requirement could become fatal. Medieval hilltop fortresses often depended on cisterns, rainwater collection, storage pits, and carefully protected wells. But at Deva, the complete system is still difficult to reconstruct from the surviving ruins. The question is not simply whether water existed. The question is how much could be stored, how it was kept clean, how leakage was prevented on fractured volcanic rock, and how long the fortress could resist if cut off from the town below. The defensive design also raises questions. Deva was not just a wall around a summit. It had multiple chambers, gates, towers, and inner zones. This meant an attacker could not simply break one barrier and control the fortress. They had to pass through controlled spaces, changing elevation exposed to defenders from several directions. The hill itself became part of the weapon. Narrow access routes slowed movement. Curved walls limited direct assault. Higher positions allowed observation and fire. The fortress was a stone system built around gravity. In modern military terms, it looks like defense in depth, but in medieval practice it came from experience, memory, and repeated adaptation to real attacks. The later history of Deva gives the structure one accidental test. During the 1848 to 1849 revolutionary period, Austrian soldiers occupied the fortress. In August 1849, an explosion in the ammunition or gunpowder storage destroyed a large part of the citadel and killed soldiers inside. Some accounts place the event on the 13th of August. For a medieval fortress, this was catastrophic. Yet parts of the walls, towers, and defensive belts survived enough to remain visible and later be restored. That survival matters. An internal explosion attacks a structure differently from a siege. It pushes outward from inside, where walls were not designed to receive the same kind of force. The remaining ruins suggest that the fortress was not a fragile shell, but a massive system tied deeply to the hill. There is another unanswered issue. How much older knowledge lies beneath the medieval fortress? Local historical descriptions say Deva was built on an earlier Dacian site, and the wider region contains traces of Bronze Age, Dacian, Roman, and medieval occupation. The Dacian word Deva itself is often associated with fortified settlements. If the medieval builders reused an older strategic place, then Deva may preserve a layered memory of defense. The 13th century fortress did not appear in an empty landscape. It rose in a region already shaped by mining, roads, valleys, and older fortified traditions. But the exact relationship between older occupation and the medieval walls remains a difficult archaeological question. Mirabriga lies on a low plateau near the modern town of Santiago do Cachem in southwestern Portugal, far from the monumental fame of Rome or Pompeii. Yet beneath its quiet ruins sits one of the most technically intriguing Roman settlements in the Iberian Peninsula. First mentioned by scholars during the Renaissance and investigated more systematically from the 18th century onward, archaeological excavations eventually revealed a remarkably well-preserved forum, 2 large bath complexes, paved streets, an exceptionally rare Roman circus, underground drainage networks, and evidence of sophisticated hydraulic engineering. What initially appeared to be an ordinary provincial town soon became an engineering puzzle. Nearly every major public building depended on a water system whose complete source has never been identified, raising a question that continues to challenge archaeologists today. How did a relatively small settlement sustain infrastructure that rivaled cities several times its size? Water is the thread connecting nearly every mystery at Mirabriga. Roman baths were among the most water-intensive public buildings ever constructed in antiquity. A single medium-sized bath complex could consume tens or even hundreds of thousands of litres of fresh water every day depending on its size and visitor numbers. Mirabriga possessed not 1 but 2 bath complexes built during different construction phases, each containing hot, warm, and cold rooms connected through an elaborate heating system. The puzzle is that no complete aqueduct feeding these facilities has ever been found. Fragments of channels and reservoirs survive, yet they do not fully explain how such enormous volumes of water reach the settlement. Unlike Pont du Gard or the aqueduct supplying Segovia Aqueduct, whose sources and routes can be reconstructed over many kilometers, Mirabriga still hides much of its hydraulic network beneath the landscape. Some archaeologists suspect that portions remain buried beneath later deposits, while others propose that local springs and carefully managed storage cisterns supplied the city through a decentralized system. Neither hypothesis completely explains the archaeological evidence. The baths themselves reveal another engineering challenge. They stand on uneven bedrock rather than a naturally level plain. Roman builders first had to reshape the terrain before constructing walls, furnaces, pools, and drainage channels. Modern laser surveys show that water channels maintain carefully controlled gradients over considerable distances. Civil engineers generally recommend drainage slopes of roughly 1 to 2% to ensure efficient self-cleaning flow while preventing erosion. Remarkably, many Roman drainage systems across the empire fall within similar ranges, and Mirabriga appears no exception. Achieving such precision without laser levels, digital surveying equipment, or modern optical instruments remains astonishing. Roman surveyors relied on tools such as the chorobates and groma, yet translating these relatively simple devices into consistently accurate hydraulic gradients across irregular terrain still impresses modern engineers. Perhaps even more remarkable is what lies beneath the floors. Like many Roman bathhouses, Mirabriga used the hypocaust, one of antiquity's most advanced heating technologies. Brick pillars, often standing less than a metre apart, supported suspended floors while hot air circulated below before rising through hollow wall tiles. This transformed the entire building into a giant heat exchanger. Temperatures inside the hottest rooms may have exceeded 40 degrees Celsius, requiring constant thermal expansion and contraction of the masonry. Despite nearly 2,000 years of earthquakes, weathering and abandonment, many of these supporting pillars remain standing. Their survival suggests an impressive understanding of load distribution. A single collapse column could have triggered progressive failure across large sections of the suspended floor, yet numerous sections still preserve their original geometry. Even today, engineers designing radiant floor heating rely on principles surprisingly similar to those demonstrated by Roman hypocaust systems. Waterproofing introduces another unresolved technological question. Pools, channels, and reservoirs at Mirabriga were coated with hydraulic mortar, capable of remaining stable despite centuries of moisture exposure. Roman hydraulic concrete has become famous because of structures such as the harbour at Portus Cosenus and marine installations near Naples, where volcanic ash known as pozzolana reacted chemically with lime to produce exceptionally durable cementitious materials. Portugal, however, lies far from the volcanic regions that supplied classic Italian pozzolana. Local builders therefore adapted their recipes using crushed ceramics, carefully selected sands, and regional limestone. Chemical analyses show that these mortars often developed dense microstructures capable of resisting water infiltration for centuries. Yet the precise mixing ratios, firing conditions for crushed brick additives, curing techniques, and quality control methods remain largely unknown. Modern laboratories can identify mineral phases through X-ray diffraction and scanning electron microscopy, but reconstructing the complete manufacturing process remains difficult because the original craftsmen left no written manuals. Another mystery emerges from the city's drainage system. Beneath the streets runs a network of underground channels carrying wastewater away from public buildings. What appears simple is actually a delicate hydraulic balance. If the slope becomes too steep, flowing water leaves heavier sediment behind, gradually clogging the channel. If it becomes too shallow, water stagnates. Roman engineers repeatedly achieved gradients close to optimal values long before fluid mechanics became a mathematical science. Unlike modern civil engineers who calculate flow using equations such as Manning's formula, Roman builders relied on practical knowledge accumulated through generations of experience. Mirabriga demonstrates that this empirical tradition reached a remarkable level of sophistication without the theoretical framework available today. The city's urban planning deepens the mystery further. Instead of expanding randomly, streets, baths, temples, workshops, and public spaces were carefully organized across sloping terrain. Every building interacted with another through water supply, drainage, transportation, and structural support. The Forum occupied the civic center, while the baths connected efficiently to the street network and drainage infrastructure. Even more unusual is the location of the circus. Roman circuses are relatively rare in Portugal, and Mirabriga possesses one of the few known examples. Rather than occupying the crowded urban core, it was constructed outside the main settlement, where the natural topography could accommodate its elongated shape, stretching roughly 400 meters in length. Why a town of modest population invested enormous resources into such a specialized entertainment complex remains debated. Some researchers argue that it served a much larger regional population, transforming Mirobrugge into an important ceremonial and commercial gathering place, rather than merely a local town. The logistics behind constructing this settlement remain equally difficult to visualize. Every limestone block had to be quarried, shaped, transported, and positioned with remarkable precision. Lime required kilns capable of reaching temperatures approaching 900 degrees Celsius. Bricks for the hypocaust demanded controlled firing, while timber supplied scaffolding, roofing, and furnace fuel. Thousands of tons of material moved across landscapes without steam engines, internal combustion vehicles, or cranes powered by electricity. Roman treadwheel cranes could lift several tons using human labor alone, but coordinating quarrying, transport, masonry, surveying, plumbing, and heating systems into a unified construction program required an administrative capacity often underestimated in provincial settlements. Above the Gauja River Valley in Sigulda, Latvia, Turaida Castle looks like a red wound cut into the forest, a medieval fortress whose bricks have survived Baltic winters for more than 800 years. The castle began in 1214, when Bishop Albert of Riga ordered a stone fortress to be built on the site of an earlier Livonian wooden stronghold. From the 13th to the 16th century, it served as one of the major castles of the archbishops of Riga, controlling land, trade, and military power in medieval Livonia. Archaeological investigation and restoration intensified in the 20th century, especially after major conservation work during the Soviet period and later museum development. Today, Turaida is often described as one of the most archaeologically studied medieval castles in the Baltic region. But the strangest part of Turaida is not its tower, its legends, or even its wars. It is the red brick itself. In Northern Europe, brick is not a forgiving material. Latvia's climate brings rain, snow, moisture, and repeated freeze-thaw cycles. When water enters the pores of a brick and freezes, it expands by roughly 9%. Over decades, this pressure can split the surface, open microcracks, and slowly turn strong masonry into powder. Modern material studies show that freeze-thaw action can seriously damage historical bricks by changing pore structure, increasing water movement, and reducing mechanical strength. One recent study found that after only 65 freeze-thaw cycles, brick pore volume increased by 23%, while average pore diameter became nearly 4 times larger. Turaida has faced not 65 cycles, but centuries of them. If one winter produces dozens of freezing and thawing events, the castle's oldest masonry may have endured thousands of attacks from ice inside the brick. Yet parts of the original medieval fabric remained strong enough to be conserved, studied, and rebuilt around. That is the first real engineering mystery. How did 13th century builders create fired clay that could survive in one of the worst environments for porous ceramic material? The answer is not as simple as saying they used good clay. Medieval brickmaking was a chain of decisions. Clay had to be dug, weathered, mixed, shaped, dried, fired, cooled, transported, and finally bonded into walls with lime mortar. A small mistake at any step could create weak bricks. Too much organic matter could burn out and leave oversized pores. Too little firing could leave the core soft and water absorbent. Too much firing could deform the brick or make it brittle. Iron compounds helped create the red color, but color alone does not prove strength. What matters is the hidden microstructure: pore size, pore connection, mineral transformation, firing temperature, and how evenly heat passed through the kiln. This is where Turaida becomes fascinating. The builders were working in 1214, without thermometers, modern kilns, chemistry, or microscopes. Yet they produced enough red brick for a major fortress around 200 meters long, developed over more than 3 centuries. The main tower today rises about 38 to 42 meters depending on measurement and restoration reference, showing the scale of vertical load these bricks were expected to carry. Every brick in such a structure had to resist not only weather, but compression, wall movement, moisture rising from the ground, and heat from later fires. The lost knowledge may have been local. The brickmakers likely understood which clay beds near the Gauja Valley behaved best after firing, which mixtures cracked during drying, which kiln zones produced stronger units, and how long the bricks needed to cool before use. This was not laboratory science, but accumulated craft memory. The mystery is that the final product sometimes performed like a material engineered for survival, even though the people making it had no written material science. The mortar deepens the puzzle. Historic masonry does not survive because bricks are strong alone. It survives when brick and mortar work together. Lime mortar is softer and more breathable than modern cement, allowing moisture to move out instead of trapping it inside the wall. Conservation studies on historic masonry show that repair mortar must respond carefully to freeze-thaw cycling, salts, thermal movement, and rain penetration. The wrong mortar can damage old bricks instead of protecting them. This means the medieval builders of Taurida may have accidentally achieved something modern restoration engineers still struggle with: compatibility. Their mortar was not just glue, it was a moisture control system. That matters because the castle suffered heavily. It lost strategic importance after the medieval period, was damaged by a major fire in 1776, and gradually became a ruin. By the 20th century, only fragments of walls and towers remained in places, yet those fragments preserved enough evidence to guide archaeological excavation and reconstruction. The survival of damaged brickwork after fire, abandonment, frost, and vegetation suggests that the original material had a durability far beyond ordinary construction. Another unsolved question lies beneath the walls. Taurida stands on a castle mound above the Gauja Valley, not on a flat modern foundation slab. Medieval builders had to manage uneven ground, slope pressure, water drainage, and heavy masonry loads using observation rather than structural calculations. A tall brick tower concentrates force downward. Defensive walls spread it sideways. Rainwater tries to enter joints. Frost tries to push the masonry apart. Yet the castle layout grew over centuries into a functioning fortified system, with towers, walls, residential spaces, and later defensive upgrades. Documents and archaeological evidence show continued building from the 13th through 15th centuries, including vaulted rooms and lime columns found in excavation. The logistics are just as mysterious. A red brick castle was not built by a few masons with a cart. It required clay extraction, kilns, fuel, timber, lime burning, sand collection, transport routes, scaffolding, water supply, and organized labor. To fire bricks, medieval workers needed high and stable heat for long periods. To make lime mortar, limestone had to be burned at intense temperature, then slaked safely with water. Each process consumed fuel. In a forested Baltic landscape, that meant the castle was not only a military structure, it was the visible peak of a hidden industrial system. And yet, much of that system has vanished. We see the castle, but not all the kilns. We see the tower, but not every clay pit. We see the finished walls, but not the full chain of measurements, experiments, failures, and corrections that made them possible. This is why Taurida is valuable as an ancient engineering mystery. It is not unexplained because aliens built it, or because its history is unknown. It is mysterious because the physical evidence shows a level of practical control that is difficult to reconstruct today in full detail. Taurida Castle was built at a frontier moment, when Christianity, crusading military power, local Livonian landscapes, and imported Baltic brick architecture collided. Its red walls were political symbols, but they were also technical machines. They managed weight, cold, moisture, fire, and time. The fact that any 13th century brickwork survived Latvia's climate for more than 800 years forces a quiet question. How much medieval engineering knowledge was never written down, only carried in the hands of workers who knew clay, heat, lime, and frost better than their own rulers did? Citania de Briteros was brought into archaeological history in the 1870s when Francisco Martin Sarmento began systematic excavations on Monte de São Romão, near Guimarães in northern Portugal. What he uncovered was not a simple hill village, but a vast Iron Age settlement overlooking the Ave River Valley. About 24 hectares in total, with roughly 7 hectares of visible excavated ruins today. The site is now considered one of the most expressive proto-historic settlements of the Iberian Peninsula, remarkable for its walls, urban layout, and architecture. At first glance, Citania de Briteros looks like a ruined city of stone circles and broken walls. But the longer we look, the stranger it becomes. This was a Castro culture settlement, built mainly before full Roman control of the region. Yet its organization does not feel random. Streets run through the hilltop in a roughly planned pattern. Residential areas, public zones, paved roads, livestock spaces, ramparts, gates and bath structures were arranged across difficult terrain. In many Iron Age settlements, architecture appears to grow outward through necessity. At Briteros, the city seems to have been negotiated with the mountain itself. The first technical puzzle is the stone. Briteros was built largely from granite, a hard igneous rock with a Mohs hardness of around 6 to 7. It is not easy material. Granite resists shaping, dulls tools, and weighs roughly 2.6 to 2.8 tons per cubic meter. A single block, only half a cubic meter in volume, could weigh well over 1 ton. Yet thousands of stones were quarried, moved, fitted and stacked across a hilltop without modern cranes, steel saws or cement. The walls were built using dry stone masonry, meaning no mortar held them together. Stability came from weight, friction, careful placement, and the silent intelligence of the builders. This matters because dry stone construction is unforgiving. If a wall leans too far, water enters. If stones are badly seated, pressure concentrates in weak points. If the foundation shifts, the structure opens and collapses. At Briteros, several ramparts still survive, and some walls are reported between 1 and 3 meters thick, with restored sections reaching almost 4 meters high. The settlement was protected by multiple defensive wall lines, including a partly preserved 4th line to the north, and these walls also shaped circulation through gates, ramps, and stairs. They were not only barriers, they were instruments of control. The question is not whether Iron Age people could build with stone. They clearly could. The question is how they controlled error at this scale. In Roman engineering, we often find written traditions, standardized military surveying, trained architects, and administrative records. At Briteros, there is no surviving manual, no construction plan, no inscription explaining who measured the walls, who chose the stone, or how labor was organized. Yet the site required quarrying, transport, road access, foundation preparation, drainage awareness, and repeated building standards across generations. The urban layout deepens the problem. Briteros was not a collection of isolated huts scattered over a hill. It contained many circular houses, some rectangular structures, paved streets, courtyards, and compounds. The settlement's acropolis occupied an elevated area of about 7 hectares, and the broader site extended over a much larger fortified zone. Some streets appear carefully arranged rather than merely worn by movement. Compared with smaller hill forts, Brateros feels almost proto-urban. Compared with Roman towns, it lacks the rigid geometry of a military grid. That middle condition is what makes it fascinating. It suggests a society that had planning principles, but not necessarily the same planning language as Rome. Then comes the hidden engineering of water. Northern Portugal is not a dry desert where ruins survive because rain rarely falls. The region has a wet Atlantic climate. On a hilltop settlement, water is both a resource and a threat. Rain running down stone streets can erode foundations, flood interiors, and destabilize walls. Yet Brateros remained occupied long enough to develop a complex built environment. Paved streets and stone compounds imply that water had to be guided, slowed, drained, or absorbed. Some channels and drainage features are known, but the complete operating system is still difficult to reconstruct. The most important parts may have vanished. Wooden covers, soil channels, organic roofing, perishable gutters, or surface treatments erased by time. The houses create another unanswered question. Many are round, a form common in Castro culture. Round buildings distribute lateral pressure efficiently and can be easier to roof with conical timber structures. But Brateros also shows rectangular and mixed forms, suggesting changing function, social difference, Roman influence, or experimentation. Roofs are the missing half of the city. Stone walls survived. Timber, thatch, and clay disappeared. Without the roofs, archaeologists must reconstruct the ancient city from its skeleton. We do not know exactly how smoke escaped, how interiors were insulated, how roofs resisted Atlantic storms, or how much woodworking expertise was required to complete what the stone foundations began. The most haunting structure at Citania de Brateros is the Pedra Formosa, the beautiful stone. It belonged to a Castro bath complex, often interpreted as a sauna or ritual bathing structure. Archaeology magazine notes that a bath complex dating before Roman annexation of the region in 19 BC was found at Brateros in the 1930s, with a decorated stone slab and evidence connected to water supplied from a nearby spring. This is where Brateros becomes more than a fortified town. If the bath was truly a steam structure, then the builders were not only shaping stone, they were managing heat, water, air, and ritual movement. Similar Iron Age sauna-like buildings are known in northern Portugal and the Cantabrian regions of Spain, but they remain under-discussed compared with Roman baths. Researchers have described them as specialized buildings found in large hill forts, possibly connected with bathing, purification, protection, and ritual practice. The technical mystery is how the system worked in practice. A steam bath requires more than a closed room. It needs controlled heating, water delivery, ventilation, drainage, and safe human access. Too much heat makes the chamber dangerous. Too little heat makes the ritual ineffective. Too much smoke makes it unusable. Too much trapped moisture damages the structure. The builders had to understand how stone stores heat, how water turns to vapor, how air moves through small openings, and how bodies experience temperature. This is practical physics, but without equations, thermometers, or written engineering theory. The Pedra Formosa itself makes the puzzle even stranger. It is not merely functional, it is decorated. Its carved front suggests that the bath was not a hidden utility, but a meaningful threshold. The person entering may have crossed from ordinary space into a controlled ritual environment. The stone worked like architecture, sculpture, and technology at the same time. In Roman baths, engineering is displayed through vaults, hypocaust floors, aqueducts, and pools. At Brateros, the technology is more compressed and more symbolic. a stone doorway, a heated chamber, water, darkness, steam, and controlled passage. Located along the southern Bug estuary in modern Ukraine, one Greek city transformed metal into a source of power. This was Olbia Pontica, a colony on the northern Black Sea where trade, coinage, and metallurgy became almost inseparable. Its ruins were not found as a buried wonder under desert sand, but as a wounded landscape near the village of Parutine. Professional excavations began in 1901 under Boris Farmakovsky, revealing walls, inscriptions, coins, workshops, and a lower city partly damaged by erosion and water. Olbia was founded by Greek colonists from Miletus in the 7th century BC. At its height, the city covered about 50 hectares, with an upper town, a lower harbour zone, sanctuaries, streets, defensive walls and workshops facing one of the most important river mouths of the Black Sea. From here, grain, fish, slaves, hides, timber and raw materials could move south toward the Greek world, while wine, oil, pottery, luxury objects and finished goods moved back towards Scythian lands. But beneath this trade network was a deeper question. How did a remote colonial city maintain the technical skill needed to turn metal into money, tools, status objects, weapons, fittings, weights and exchange goods for centuries? Olbia was not just a port, it was a machine for transforming resources into trust. The most famous clue is strangely small, the bronze dolphin money of Olbia. Around the late 6th century BC, the city began producing cast bronze objects shaped like leaping dolphins. They were not ordinary round coins struck with dies like many Greek currencies. They were cast, repeated, recognizable, and tied to the cult of Apollo Delphinios. Their shape looked symbolic, but their function was practical. They allowed value to circulate in a frontier market where Greeks, Scythians, merchants, sailors, farmers, and craftsmen all needed a common language of exchange. This is where the metallurgy becomes mysterious. Casting hundreds or thousands of small bronze dolphins required more than artistic imagination. It required a stable alloy, repeated molds, controlled melting, predictable cooling, and enough standardization for people to accept the objects as money. Bronze normally requires copper mixed with tin or other elements. Copper melts at about 1085 degrees Celsius, while bronze can be cast at slightly lower working temperatures depending on the alloy. Achieving that repeatedly in small furnaces using charcoal, bellows, clay crucibles, and human judgment was not simple. A few degrees too low, and the metal would not flow cleanly into the mold. Too much oxygen, and the surface could become flawed. Too much impurity, and the object could crack, shrink, or vary in weight. The mystery is not that ancient people could melt metal. Many cultures did. The mystery is how Olbia turned that skill into a commercial system. A single craftsman can make one beautiful object. A trading city needs repeatable production. It needs metal suppliers, fuel, mold makers, furnace operators, inspectors, merchants, and people who understand weight, purity, and trust. Yet the full technical chain has not survived. We have the coins, the fragments, the tools, the slag, and the archaeological context, but not the operating manual. Some excavations show how dense this monetary world was. In the T4 sector of Olbia, research from excavations in 2018 to 2020 recorded 154 coins, with about half of them being dolphin-shaped pieces. One hoard included 26 cast dolphin coins together with bronze items. That kind of find suggests that the dolphins were not isolated ritual curiosities. They were part of daily accumulation, exchange, and storage. The same city also produced larger cast bronze coins. Some 5th century Olbian bronze issues were massive compared with ordinary pocket money. One type reached about 69 millimeters in diameter and roughly 136 grams in weight. A coin that large is not convenient for casual use. It looks closer to a heavy unit of civic value, almost a metal statement. It raises a technical problem. Casting a large bronze disc evenly is harder than casting a tiny token. The metal must enter the mold without freezing too early, air must escape, the surface must cool without destructive stress, and the final object must remain recognizable enough to be accepted. Olbia's metal economy probably depended on both local and imported resources. The northern Black Sea region offered access to steppe networks, river routes, and contact with communities that could supply hides, animals, grain, and possibly raw materials. But tin, high-quality copper, and certain finished goods often moved through long-distance trade. That means Olbia's metallurgists were working inside a supply chain that stretched far beyond the city walls. The technical challenge was not only heating metal, it was managing inconsistency. Different copper sources can contain different traces of arsenic, lead, silver, nickel, or iron. Different fuel quality changes furnace temperature. Different crucibles affect contamination. Still, the finished objects had to be reliable enough for commerce. This creates one of Olbia's strongest ancient engineering questions. How did its workshops judge metal quality without modern chemical analysis? They had no spectrometer, no digital thermometer, no industrial furnace gauge. Their tools were color, sound, weight, smell, surface texture, fracture behavior, and experience. A skilled founder could read the glow of a melt, the fluidity of the pore, the skin forming on the surface, and the sound of a cooled object when struck. This was a scientific system without written formulas, transmitted by practice rather than textbooks. The harbour made that system valuable. Olbia's lower city, now partly submerged or eroded, was closely connected with docking, storage, and craft activity. Studies of the harbour area use inscriptions, graffiti, architectural remains, and finds from the lower city to reconstruct how the port functioned. Yet the artificial harbour facilities are only partly understood. If goods arrived by river and sea, metal objects had to be produced, weighed, repaired, exchanged, and possibly recycled near the commercial zone. Broken tools could become scrap. Scrap could become new bronze. Coins could move into hoards, temples, markets, or foreign hands. In such a world, metallurgy was not a separate craft. It was the nervous system of trade. The city's position made this even more complex. Olbia stood between the Greek world and the Scythian steppe. Greek merchants understood coinage, contracts, temples, and civic identity. Steppe elites valued metal differently, as weaponry, ornaments, horse gear, status display, and portable wealth. Olbia had to speak both languages. Its metallurgists may have produced objects that were technically Greek, but commercially adapted to frontier exchange. The dolphin money itself reflects that hybrid world, sacred symbol, civic marker, and practical bronze object at the same time. The archaeological record also suggests a wide craft environment. Olbia had potters, masons, woodworkers, metalworkers, and traders. These crafts supported one another. Potters could produce ceramic molds or furnace parts. Woodworkers supplied handles, bellows frames, ship repairs, and packing material. Masons built workshops and hearths. Traders brought ore, scrap, ingots, tools, and foreign models. Every bronze dolphin was therefore the final visible result of many invisible trades. What remains unexplained is the level of coordination. A metal workshop needs charcoal in large quantities. Charcoal production requires wood and controlled burning. Furnaces need clay linings that can survive repeated thermal shock. Bellows require leather and carpentry. Crucibles must resist heat and chemical attack. Molds must be prepared, dried, fired, and broken or reused. If the city produced coinage across generations, then Olbia had an industrial rhythm, even if it did not look like a modern factory. There is also the problem of trust. In any ancient marketplace, metal could deceive. A bronze object might look valuable but contain too much lead. A silver coin could be plated, a weight could be slightly wrong, a cast token could be copied. For Olbia's metal money to function, people needed confidence in the issuing authority, the symbol, the alloy, and the expected value. This means metallurgy was tied to law, religion, and civic power. The Temple of Apollo Delphinios, the dolphin symbol, and the city's commercial identity may have worked together to make metal believable. Over time, Olbia changed. It survived wars, pressure from surrounding peoples, economic shifts, and Roman influence. The city lasted from the archaic Greek period into the 4th century AD, but its most distinctive technical traditions did not survive as living systems. The harbour deteriorated, the lower city was damaged by water and erosion, workshops disappeared, the people who knew the alloy recipes, furnace behaviour, mould preparation, and commercial rules vanished without leaving a full written explanation. A city was built on soft coastal ground beside the Taman Peninsula of southern Russia, where land, sea, mud, and underground water never stayed still. That city was Phanagoria. It was founded around 543 BC by Greek colonists from Teos, and later became one of the most important cities of the Bosporan Kingdom. Ancient sources described it as a major trading centre between the Black Sea, the Sea of Azov, the Caucasus, and the steppe world. At its height, Phanagoria covered about 65 to 75 hectares, with houses, streets, temples, defensive walls, workshops, burial grounds, and a harbour system. Today, roughly 1/3 of the ancient city is underwater, while the rest lies near the modern village of Sinoi. That fact alone turns Phanagoria into more than a ruin. It is a test case in ancient engineering. The site was recognised in the 18th century when marble statue bases with dedications to Aphrodite were found in the area. Archaeological work began in 1822, after soldiers opened a burial mound and uncovered rich objects of gold and silver. Later excavations revealed a vast necropolis, city blocks, inscriptions, pottery, coins, fortifications, and submerged remains. Modern research has shown that Phanagoria was not a small colony clinging to the coast. It was a long-lived urban machine, surviving for more than 1,000 years in one of the most unstable environments a builder could choose. The central question is not simply why the Greeks came here, it is how they managed to build here at all. The Taman Peninsula is not a clean block of bedrock. It is a restless landscape shaped by sea level change, estuaries, clay, sand, shells, mud volcanoes, coastal erosion, and groundwater. In modern engineering, this kind of ground is treated with caution. Soft, saturated soil can compress under weight. Sand can shift. Clay can swell or shrink. Saltwater can attack mortar. Foundations can settle unevenly, causing walls to crack, floors to tilt, and buildings to fail. Yet Phanagoria carried stone architecture, street grids, storage buildings, public spaces, and defensive structures across centuries. This is where the mystery becomes technical. A large ancient city is not heavy in one place. It spreads thousands of tons of load across the ground. Every wall presses downward. Every roof adds weight. Every storage room filled with grain, amphorae, or cargo increases pressure on the soil. If a district is built on mixed layers of clay, sand, and marine sediment, one part may sink faster than another. Even a few centimeters of differential settlement can damage masonry. Modern builders solve this with soil testing, concrete piles, drainage membranes, geotextiles, and calculated foundation mats. Phanagoria had none of those tools. and yet its builders appear to have understood the ground through experience. The most likely solution was not one invention, but a system. They may have chosen higher natural terraces for heavier buildings and kept lighter structures on lower, wetter ground. They probably used layers of stone, rubble, compacted earth, ceramic fragments and sand to spread weight and drain moisture. Broken pottery was not waste in the ancient world. It could become a hard, breathable layer beneath floors. Stone packing could reduce direct contact between walls and saturated soil. Raised floors could protect living areas from seasonal damp. In other words, Phanagoria may have survived because its foundations were not rigid in a modern concrete sense. They were layered, draining, and adaptable. That possibility makes the city more impressive, not less. A rigid foundation on unstable soil can crack when the ground moves. A carefully prepared ancient foundation, made of stone, rubble, clay, and packed fill, could tolerate slow movement. It did not defeat nature. It negotiated with it. The underwater remains make the problem even stranger. Ancient Phanagoria once stood on two terraces descending toward a gulf. Over time, the coastal part of the city and its port were submerged by Black Sea transgression and covered by seabed sediments. Archaeological reports describe architectural fragments and harbour-related material underwater. A Hellenistic shipwreck was discovered near the ancient shoreline in 2012, showing how close maritime activity was to the city itself. This was not a symbolic coastal settlement. It was a working port where land engineering and sea engineering had to function together. For a port city, foundation stability was only half the battle. Water had to be controlled from above, below, and beside the city. Rainfall had to move through streets. Groundwater had to escape from beneath buildings. Wastewater had to be removed. Harbour zones had to resist erosion and silting. On the Taman coast, sediment is constantly reworked by waves, currents, and changes in shoreline. A poorly designed harbour would choke with silt. A badly drained lower town would become damp and unhealthy. If Phanagoria functioned as a major emporium for centuries, its builders must have learned how to guide water without creating catastrophic erosion under their own walls. This is one of the least visible forms of ancient technology. Grand temples impress the eye, but drainage keeps a city alive. A street that slopes by only 1 or 2 degrees can decide whether water leaves or pools. A buried drain must be low enough to collect runoff, but strong enough not to collapse. A foundation trench must release water without washing away the soil that supports it. These are not mysteries of magic. They are mysteries of practical measurement. Greek surveyors had simple instruments: ropes, rods, plumb lines, sighting tools, and water levels. But the results at sites like Phanagoria show that simple tools could produce complex urban decisions. Streets, terraces, buildings, and drainage routes had to be coordinated before construction. If one district was raised, water would flow into another. If a wall blocked natural runoff, pressure would build behind it. The city therefore required planning not only in space, but in time. Builders had to predict what would happen during rain, winter, coastal flooding, and long-term settlement. The deeper problems that Phanagoria was not built once, it evolved. A city founded in the 6th century BC and active into late antiquity accumulates layers. Old floors are buried, new buildings rise over earlier walls, streets are repaired, drainage routes are modified, ground level slowly climbs. Archaeologists estimate that the cultural deposits at Phanagoria amount to millions of cubic meters. This means the city became its own artificial ground. Its inhabitants were not only living on nature, they were living on centuries of compressed human activity: ash, clay floors, broken pottery, stone rubble, demolished walls, and rebuilt surfaces. That artificial ground may be the hidden engineering secret. In many ancient cities, repeated occupation created stable platforms. Each rebuilding episode added compacted material. Each fire or collapse created a new base. Over generations, the city thickened. Phanagoria's builders may have used this process deliberately, raising vulnerable zones and turning occupation debris into foundation mass. What looks like ruin today may once have functioned as slow urban reinforcement. But there are still unanswered questions. How did they decide which soils could carry heavier buildings? Did they recognize dangerous wet layers by smell, color, plant growth, or the behavior of test pits? Did they use timber reinforcement in places now destroyed by decay? Were some harbor structures built on wooden piles that have vanished? Did they mix local lime mortars differently for damp coastal zones? The surviving evidence gives fragments, not a full manual. The masonry itself adds another layer to the puzzle. Phanagoria's walls were built with local stone and unworked or roughly worked blocks in some phases. This was practical, but it required skill. Irregular stones do not automatically make strong walls. They need careful selection, bedding, packing stones, and mortar that can absorb slight movement. In unstable ground, perfect rigidity may be dangerous. A wall that can tolerate small shifts without sudden collapse is better than a brittle one. The endurance of surviving structures suggests that Phanagoria's builders understood this balance. Then there is the question of logistics. A city of 65 to 75 hectares could not be built casually. Stone, timber, lime, clay, roof tiles, metals, food, labor and tools had to arrive continuously. Some materials came by sea, others from inland routes. Every amphora, beam and block had to be moved without engines, cranes or trucks. The harbour was therefore not only an economic feature, it was part of the construction system. Without it, the city could not maintain itself. The sinking of part of Phanagoria gives the story its final mystery. If about 1/3 of the city is now submerged, then the shoreline did not merely move on a map. It transformed the archaeological record. Buildings that once stood in air became underwater remains. Streets became seabed. Harbour zones disappeared beneath sediment. This process preserved some materials while destroying others. Stone survived. Organic structures may have vanished. Wooden engineering, if it existed, may be missing from the evidence. That absence is important. What we cannot see may have been essential. Hidden among the hills of northeastern Portugal near the modern town of Marvão lies the ancient Roman city of Amaya, far removed from the well-known capitals that dominate historical narratives. For centuries, almost nothing visible remained. Farmers unknowingly ploughed over buried streets, forums, baths and houses, while countless stone blocks had been carried away to build medieval villages. Only in the late 20th century did archaeologists begin to understand what had been hiding beneath the fields. Traditional excavation revealed only scattered ruins, but everything changed when the ground-penetrating radar, magnetometry, aerial photography, LiDAR and three-dimensional digital mapping were combined. Instead of uncovering isolated buildings, scientists discovered the ghost of an entire Roman city still preserved underground. More remarkably, most of it remains unexcavated today. The buried plan revealed one of the best preserved examples of Roman urban design in the Western Iberian Peninsula, raising an uncomfortable question. If modern technology can now detect the city without moving a single stone, how accurately had Roman engineers surveyed the landscape nearly 2,000 years ago, using nothing more than simple instruments? That question becomes increasingly mysterious once the city's layout is examined. Amaya occupied roughly 25 hectares, equivalent to about 35 modern football fields, yet it was not built across a flat plain like many Roman colonial foundations. Instead, the settlement stretched across an uneven valley surrounded by hills, seasonal streams, and varying elevations. Modern engineers know that constructing a regular street grid on sloping terrain is significantly more complicated than building on level ground because every change in elevation affects drainage, foundation stability, and transportation. Nevertheless, radar surveys reveal remarkably straight streets intersecting at consistent angles, public buildings positioned along carefully planned axes, and neighborhoods organized with surprising geometric precision. Roman surveyors are known to have used instruments such as the groma for right-angle alignment and the chorobates for measuring gradients, but surviving descriptions of these devices appear deceptively simple compared with the accuracy preserved beneath a Maya. Even today, archaeologists cannot fully reconstruct the surveying sequence that transformed a naturally irregular valley into an organized urban landscape with so little accumulated error. The city's water system deepens the mystery. Unlike famous Roman settlements established beside major rivers such as Londinium on the Thames or Colonia Agrippina on the Rhine, Amaya possessed no large permanent river capable of supplying a growing urban population. Yet archaeological excavations have uncovered public baths, fountains, drainage channels, water tanks, and pressurized distribution pipes, all requiring a reliable hydraulic network. Roman urban populations typically consumed between 100 and 300 litres of water per person each day where aqueduct systems existed. Even allowing for a relatively modest population of perhaps 4,000 to 6,000 inhabitants, Amaya would still have required hundreds of thousands of litres daily. Researchers have identified fragments of channels and storage structures, but no complete reconstruction explains exactly how water entered, circulated through, and exited the city. Was groundwater exploited more efficiently than currently believed? Were seasonal springs regulated through hidden reservoirs? Or did an aqueduct survive only in fragments too small to recognize? Despite decades of investigation, the complete hydraulic blueprint remains missing. Even more impressive is what happened after the water entered the city. Amaya's drainage network still demonstrates gradients carefully calculated to allow wastewater to flow naturally without modern pumps. Civil engineers know that gravity-fed sewers require slope steep enough to prevent sediment accumulation, yet shallow enough to avoid excessive erosion. A deviation of only a few centimeters over long distances can gradually produce stagnant water or structural failure. Roman builders obviously understood these principles through experience rather than modern fluid dynamics, but exactly how they maintained such consistency across an uneven landscape remains uncertain. Similar questions surround larger Roman engineering achievements, including the aqueducts of Segovia and Pont du Gard, whose gradients often vary by only a few centimeters per kilometer. Amaya demonstrates that this remarkable hydraulic precision extended even to comparatively remote provincial towns. Stone construction presents another unresolved technological puzzle. Much of Amaya was built using local granite, one of the hardest commonly available building stones, with a compressive strength often exceeding 150 megapascals. Granite is notoriously difficult to quarry because fractures rarely develop in predictable directions. Yet numerous surviving blocks display remarkably flat faces, sharply defined edges, and joints fitted closely enough that only thin mortar layers were required. Roman quarrying techniques involving iron wedges, wooden expansion wedges soaked with water, chisels and hammerstones are well documented elsewhere, but reproducing Amaya's construction quality using only those tools demands extraordinary craftsmanship. Experimental archaeology has demonstrated that splitting granite by controlled wedge placement is possible, yet maintaining consistent dimensional accuracy across thousands of blocks remains immensely labor-intensive. The mystery may not lie in unknown machines, but in a level of practical skill that modern industry has largely replaced with powered equipment. The city's southern gate illustrates this engineering philosophy particularly well. Excavations reveal carefully balanced masonry designed not only to support enormous stone loads, but also to withstand centuries of weathering, minor ground movement, and repeated human use. Every arch, threshold, and supporting wall depended upon precise weight distribution. Unlike reinforced concrete, Roman masonry relied almost entirely on geometry. Compression carried the loads. Every misplaced block increased the risk of long-term instability. Similar principles allowed the massive arches of the Colosseum and the Pantheon to survive for nearly 2 millennia, yet Amaya demonstrates that these structural concepts were not limited to imperial monuments. Provincial engineers had mastered the same understanding of force, balance, and material behavior. Modern archaeological technology has added another layer of mystery rather than solving the old ones. Ground-penetrating radar has mapped extensive neighborhoods never excavated. Magnetometry has revealed buried walls invisible from the surface. LiDAR surveys have detected subtle earthworks almost erased by centuries of agriculture. Digital terrain models show streets, courtyards, workshops, and public buildings extending well beyond the traditionally excavated core. In many archaeological sites, excavation is the primary source of discovery. At Amaya, however, non-invasive technology has revealed far more than excavation itself. Ironically, scientists now possess increasingly detailed digital maps of structures they have never physically uncovered. Every new survey expands the known city while simultaneously increasing the number of unanswered questions. Perhaps the most surprising discovery concerns urban administration rather than architecture. Building Amaya required enormous logistical coordination hidden beneath every visible wall. Granite had to be quarried, transported, shaped, and positioned. Lime had to be burned in kilns at temperatures approaching 900 degrees Celsius to produce mortar. Timber supported scaffolding, roofing, lifting frames, and construction equipment. Ceramic pipes, roof tiles, bricks, and drainage elements required specialized workshops operating continuously. Food, tools, animals, laborers, surveyors, and administrators all had to function together according to carefully planned schedules. Modern supply chain analysis shows that large construction projects often involve far more invisible organization than visible architecture. Amaya suggests that even a provincial Roman city possessed administrative systems capable of coordinating thousands of individual operations with remarkable efficiency, yet almost none of those administrative records survive. At the mouth of the Dniester estuary in southwestern Ukraine, beneath the shadow of Bilhorod-Dnistrovsky Fortress, lies Tiras, a Greek city built where land, river, and sea never stopped moving. It was not discovered like a lost city in the desert. Its remains slowly emerged through excavations around the medieval fortress, where archaeologists realized that the later walls were standing over a much older Greek and Roman settlement. Tyros was founded by colonists from Miletus around the late 6th century BC, on the right bank of the Dniester estuary, roughly 10 to 12 kilometers from the Black Sea. By the 4th century BC, it had become a prosperous trading center, minting its own coins and connecting the Mediterranean world with the steppe societies north of the Black Sea. But Tyros was never an easy place to build. Unlike cities placed on dry hills or protected stone plateaus, this settlement stood beside an estuary, a living landscape shaped by river sediment, wind, seasonal flooding, shifting shorelines, and the slow pressure of the Black Sea. Modern geology shows how unstable this region can be. The Dniester still carries enormous amounts of sediment into the estuary. One recent geological study gives the modern annual sediment discharge of the Dniester at about 2.28 million tons. For an ancient harbour, that number changes everything. It means the same river that made Tyrus rich could also bury its port. This is where the engineering puzzle begins. Tyrus depended on maritime trade, yet it stood in one of the worst possible environments for a long-lasting harbour. A normal rocky coast gives builders a fixed edge. A deep natural bay can protect ships from waves, but an estuary is different. It breathes, it fills, channels migrate, sandbars grow, mudflats appear where boats once passed. If the ancient port of Tyrus was not constantly managed, it could have become useless within generations. And still, the city survived for centuries. The evidence points to a community that understood water far better than the ruins reveal. Tyrus traded grain, wine, fish, and other goods. Its coin imagery and inscriptions are closely connected with commerce. During the Roman period, it was important enough to host a small unit of the classis Flavia Moesica, the Roman fleet of Lower Moesia. In AD 201, Septimius Severus and Caracalla granted the inhabitants the right of duty-free trade, a rare privilege that only makes sense if Tyrus remained commercially valuable. Yet the physical remains of its harbour are fragmentary. Much of the ancient city lies under later medieval construction, and parts of the waterfront may have been destroyed, buried under sediment, or shifted away from the original shoreline. That absence is the mystery. How did an ancient city keep access to navigable water in a place where nature was constantly trying to erase the harbour? One possibility is that the engineers of Tyrus did not fight the estuary directly. They may have worked with it. Instead of building a massive exposed seaport like those on the Aegean, they likely used protected channels, natural inlets, wooden quays, reinforced banks, and landing zones that could be repaired or relocated as sediment accumulated. This kind of harbour would leave fewer stone remains than a monumental breakwater, but it would be perfectly adapted to a river mouth environment. The technology was not only stone construction, it was environmental reading, knowing where the current slowed, where mud collected, where boats could approach during different seasons, and where erosion had to be stopped before it reached the urban edge. The hardest problem was erosion. Every estuary has two enemies at once. The river deposits sediment, slowly blocking channels, while waves and storms attack exposed banks, cutting away the shoreline. To protect a working port, Tyrus needed some form of bank stabilization. Ancient builders could have used timber piles, stone packing, brushwood layers, clay embankments, or revetments placed along vulnerable edges. These materials often decay or disappear, especially in wet sediment, which may explain why the engineering is difficult to reconstruct today. What remains is the result: a city that continued to function across Greek, native, Roman, and late antique phases. The location also created a deeper technical challenge. A harbour is not just a place to tie boats, it is a machine for moving weight. Amphorae, grain sacks, timber, stone, fish products, metal goods, and wine all had to pass through a controlled space. That required level surfaces, storage areas, roads, drainage, and access between the waterfront and the upper city. If the ground was too soft, carts would sink. If water pooled, goods would rot. If the bank collapsed, the city would lose its trade artery. So the port of Taras must have depended on layers of preparation invisible to the casual eye. Compacted earth, stone bedding, retaining structures, and repeated resurfacing. The mystery becomes sharper when we remember that Tyrus was far from the old Greek mainland. It was a frontier colony more than 1,000 kilometers from Miletus by sea routes. Yet it reproduced the logic of a Greek polis: civic institutions, coinage, commercial networks, and urban planning. Its government included archons, a council, a popular assembly, and officials known from inscriptions and numismatic evidence. This suggests that engineering knowledge also travelled with the colonists, not as written manuals, but as practical experience carried by surveyors, shipmen, builders, merchants, and craftsmen. The surrounding landscape may explain why Tyrus never became archaeologically simple. Modern Bilorod-Dnistrovsky occupies the same strategic ground. The medieval fortress, known in different periods as Akerman, Cetatea Alba, or Maracastro, reused the old defensive position above the estuary. Because the later fortress covered the ancient settlement, only limited parts of Tyrus are visible today. This means the most important engineering evidence may still be hidden under walls, roads, or deeply buried waterfront deposits. There is also the question of the shoreline change. Studies of the northern Black Sea have shown that relative sea level changes and coastal submersion affected archaeological landscapes across the region. For Tyrus, even a modest change in water level or sediment balance could shift the usable waterfront. A quay that once stood beside navigable water could later sit inland. A landing place could disappear under silt. A defensive wall could become separated from the shoreline it was built to protect. This may be why the ancient port is so difficult to map with certainty. The city's builders also faced a material problem. The estuary did not provide unlimited high-quality building stone. Any durable stone used in walls, public buildings, or harbour reinforcement had to be quarried, transported, unloaded, shaped, and placed with care. River transport helped, but it created another dependency. Heavy materials had to arrive through the same unstable water system the city was trying to control. The port was therefore both the solution and the vulnerability. Tyrus was damaged several times. It was destroyed by the Getae around the 1st century BC, restored under Roman influence in the 1st century AD, and later partially destroyed during Gothic attacks after the reign of Alexander Severus. Archaeological evidence suggests Roman life continued there until the late 4th century AD. But the city did not vanish in one clean catastrophe. It was layered over, renamed, rebuilt, and absorbed into later fortifications. That slow transformation makes its lost engineering even harder to see. Tongabriga lies quietly in the granite hills of northern Portugal, near the modern town of Freixo in the Tamega Valley. Unlike Pompeii, it was never buried by volcanic ash. Unlike Rome, it never became a capital. It simply faded away, leaving behind a Roman town whose streets, baths, forum, and houses remained hidden beneath farmland until systematic archaeological excavations began during the late 20th century. What emerged surprised researchers. Instead of an ordinary provincial settlement, they uncovered a remarkably sophisticated urban landscape built directly onto one of the most difficult geological foundations in Western Europe. Nearly 2,000 years later, many of its engineering solutions still resist complete explanation. The first mystery begins beneath the city itself. Tongabriga was constructed on hard granite bedrock rather than soft sediment or river plains, where most Roman towns expanded with relative ease. Granite is among the hardest common building stones, measuring between 6 and 7 on the Mohs hardness scale, far more resistant than the limestone widely used throughout Italy. Even today, quarrying and levelling granite hillsides requires heavy machinery, diamond-cutting equipment, and precise surveying instruments. Yet Roman engineers transformed this uneven landscape into an organised town, with straight streets, public buildings, drainage systems, and residential blocks that remained structurally stable for nearly 20 centuries. Archaeologists can observe the finished result, but much of the construction process has vanished. The tool marks left on exposed bedrock reveal repeated cutting, trimming, and levelling, yet they do not fully explain how surveyors maintained such consistent elevations across an irregular granite ridge without modern optical instruments or laser levels. Roman sources describe devices such as the asterisk, groma asterisk, and asterisk chorobates. Asterisk for alignment and levelling, but translating these relatively simple instruments into the remarkable precision visible at Tonga remains difficult to reconstruct experimentally. That precision becomes even more impressive when compared with other Roman cities. At sites such as Pompeii or Ostia, builders frequently relied on broad, relatively flat volcanic plains. Even at Coimbriga, another famous Roman settlement in Portugal, much of the terrain proved easier to organise than Tonga fractured granite landscape. Here, instead of forcing the land into an ideal Roman grid, engineers subtly adapted the streets to the terrain. Many roads appear straight from above, yet detailed surveys reveal gentle curves and slight angular shifts that follow natural bedrock formations almost perfectly. This suggests that Roman planners were not merely imposing standardized urban designs across the empire. They were modifying an engineering template to exploit local geology with extraordinary efficiency. The exact mathematical methods used to achieve this adaptation remain unknown because no construction plans or technical manuals describing the process have survived. Water introduces another mystery. Roman civilization depended upon reliable hydraulic engineering. Across the empire, aqueducts carried millions of litres of water every day into cities such as Rome, where estimates suggest peak daily consumption exceeded 1 million cubic metres. Tonga, however, lacks the monumental aqueducts that dominate many Roman archaeological sites. Despite this, excavations have uncovered an extensive public bath complex containing the classic sequence of asterisk frigidarium asterisk, asterisk tepidarium asterisk, and asterisk caldarium asterisk. Such facilities demanded continuous supplies of clean water alongside carefully controlled drainage capable of removing wastewater without contaminating fresh sources. Yet the surrounding landscape offers no obvious large river capable of feeding such infrastructure directly. Archaeologists have proposed several possibilities, including springs emerging through fractured granite, underground aquifers, rainwater harvesting systems, or combinations of all three. Geophysical surveys indicate that additional hydraulic structures may still remain buried beyond the excavated sectors, but until larger portions of the settlement are exposed, the complete water network remains largely hypothetical. Even more intriguing is what cannot easily be seen. Many Roman cities preserve massive underground sewers large enough for maintenance workers to enter. At Tonga, by contrast, the drainage network appears surprisingly discreet. Rainfall in northern Portugal often exceeds 1,000 millimeters annually, considerably wetter than central Italy. Under such conditions, poorly designed streets would rapidly erode, foundations would settle unevenly, and standing water would threaten buildings. Yet the excavated roads show remarkably limited evidence of catastrophic water damage, despite centuries of exposure before burial. Some researchers suspect Roman engineers deliberately exploited natural fractures within the granite itself, transforming geological weaknesses into invisible drainage channels. If correct, this would represent an elegant form of engineering that combined artificial construction with natural rock formations rather than replacing them entirely. Unfortunately, many of these potential channels remain inaccessible beneath later deposits, leaving the hypothesis only partially tested. The bath complex raises another unanswered question concerning energy rather than water. Like major Roman bathhouses elsewhere, Tonga employed a hypocaust heating system in which hot air circulated beneath raised floors supported by hundreds of small brick pillars. Maintaining temperatures suitable for bathing required furnaces burning continuously for long periods. Experimental archaeology demonstrates that Roman baths could consume astonishing quantities of firewood, sometimes several tons every day depending on their size and frequency of use. Northern Portugal possessed extensive forests during antiquity, but supplying fuel on this scale required organised woodland management, transportation networks, labour specialisation, and long-term planning. Curiously, archaeologists have yet to identify large fuel storage areas or industrial wood processing zones corresponding to centuries of intensive operation. The baths clearly functioned, yet much of the logistical system that sustained them has disappeared from the archaeological record. The streets themselves reveal another engineering puzzle. Many surviving paving stones remain tightly aligned despite nearly 2,000 years of seasonal rainfall, temperature fluctuations, root growth, and geological movement. Modern road engineering relies upon carefully graded foundations, consisting of multiple layers of crushed stone with different grain sizes to distribute loads efficiently. Ancient Roman road manuals describe similar principles, while excavated imperial highways often contain several structural layers beneath the visible paving. At Tongabriga, however, engineers had to construct these layered foundations directly atop fractured granite instead of compacted soil. In some locations, bedrock itself appears to have served as the lowest structural layer after careful reshaping. This hybrid approach between excavation and natural foundation remains difficult to replicate because many subsurface layers remain hidden beneath intact paving. Another fascinating mystery concerns urban continuity. Archaeological evidence indicates that Tongabriga developed gradually between the 1st and 4th centuries AD. New buildings replaced older ones, public spaces expanded, and domestic neighbourhoods evolved over several generations. Yet despite centuries of construction, the city's streets, elevations, drainage routes, and architectural alignment remained remarkably coherent. Modern urban planners often struggle to maintain consistency even across a few decades of expansion. The Roman builders achieved it over centuries without satellite positioning, digital mapping, or computerized design software. This suggests the existence of highly organized surveying traditions and administrative systems capable of preserving engineering knowledge across multiple generations. Unfortunately, the documents describing these procedures, if they ever existed locally, have not survived. Granite itself presents one final technical mystery. Many of Tongabriga's architectural blocks display carefully squared faces and remarkably accurate joints, despite the stone's exceptional hardness. Experimental studies suggest that Roman masons combined iron chisels, stone hammers, wedges and controlled fracture techniques rather than attempting continuous cutting. However, granite rapidly dulls iron tools, requiring frequent sharpening or replacement. Large-scale quarrying therefore depended upon efficient metallurgy, capable of producing durable steel edges in significant quantities. Curiously, no major quarry directly associated with Tongabriga has yet revealed the full production sequence behind these construction materials. Whether blocks were shaped primarily at distant extraction sites or finished near the city remains uncertain. On the western shore of the Oslofjord in Vestfold, Norway, a field of grass hides one of the strangest royal landscapes of the Viking world. This is Borøya Mounds, a cemetery of monumental burial mounds built between the late Nordic Iron Age and the Viking Age, roughly AD 400 to 1050. Today, several huge mounds still rise from Borøya National Park, some measuring more than 45 meters across and up to 6 meters high. UNESCO's tentative listing describes the cemetery as covering about 182,000 square meters, with large and small mounds, cairns, and one of the earliest excavated Viking ship graves in Norway. The site was not discovered in one dramatic moment. It was known locally for centuries, but In 1852, one mound was excavated and revealed something extraordinary: the remains of a ship burial. The wood had mostly disappeared, yet iron rivets and grave objects showed that a real vessel had once been placed beneath the earth. Later surveys using airborne laser scanning and ground-penetrating radar showed that Bora was not just a cemetery, but a planned ritual landscape with hidden buildings, buried structures, and possibly more ship graves still underground. The deepest mystery of Bora is not only why powerful people were buried here, it is how a seafaring culture turned shipbuilding into an engineering language of death. A Viking ship was not a simple wooden object. It was a flexible machine built for waves, speed, cargo, and war. In burials like Bora, the ship was dragged onto land, placed inside a prepared grave, filled with the dead and ritual objects, then sealed under thousands of tons of earth. What remains underground is often not the ship itself, but its technological fingerprint: rows of iron rivets, stains in the soil, and the ghost-shaped outline of a hull. The Bora ship excavated in 1852 is considered the first Viking ship ever excavated in Norway. Reports suggest the vessel may have been more than 17 meters long, although the timber had decayed. That absence is part of the mystery. Archaeologists had to reconstruct the ship from rivets, impressions, and the logic of Viking boat construction. Each rivet marked where two wooden planks once overlapped. Each corroded iron fragment became a coordinate in a vanished machine. The technology behind these ships is known as clinker construction. Instead of placing planks edge to edge, Viking shipwrights overlapped them like scales. The planks were fastened with iron rivets and roves, creating a hull that was both strong and flexible. This mattered because a rigid hull can crack under northern seas, while a flexible hull can twist with the waves. The result was a vessel light enough to be pulled onto shore, yet strong enough to cross open water. The scientific mystery is how Viking builders achieved this precision without blueprints, steel measuring systems, or modern shipyards. The planks had to be chosen from suitable trees, split along the grain, shaped thin enough for speed, and curved into a hull form that balanced stability and movement. A mistake of only a few centimeters could change how the ship handled water. Yet Viking ships such as the Oseberg and Gokstad vessels show extremely advanced construction principles, and Bora belongs to the same maritime tradition. The buried ship at Bora suggests that this knowledge was not experimental. It was already elite technology, mature enough to become part of royal funerary ritual. The iron rivets are another clue. A large Viking ship could require thousands of rivets. Each one had to be forged, heated, shaped, inserted through overlapping planks, and clenched on the inside. This means Bora was connected to a wide production system: smiths, charcoal burners, ore suppliers, carpenters, rope makers, and transport workers. The ship in the grave was not just a symbol of travel to the afterlife. It was a compressed record of an entire technological economy. There is an unresolved question hidden in this process. Did Viking builders design ships by calculation or by inherited body memory? Modern engineers use drawings, hydrodynamic testing, and computer simulation. Viking shipwrights worked with eyes, hands, templates, and generations of experience. They understood how oak bends, how iron behaves under stress, how a hull flexes when pulled by waves, and how weight must be distributed. None of this knowledge was written down. It survived only in practice, and when the ship was buried, part of that knowledge was buried with it. Bora turns this question even darker because the ship was not preserved like the Oseberg or Gokstad ships. It vanished. The earth kept the metal but consumed the wood. What archaeologists see as a negative image, the missing body of a machine. From that absence, they infer length, shape, construction method, and status. It is like trying to understand an engine from the bolts left after the metal is dissolved. The burial itself required engineering. A ship more than 17 meters long could not simply be placed into a random hole. The grave had to be prepared, the vessel positioned, ritual goods arranged, and the mound built over it without collapsing the structure too early. Soil had weight, moisture changed pressure, organic materials decayed, yet the mound had to remain visible for centuries. At Boré, some surviving mounds are still monumental after more than 1,000 years, with diameters ranging from roughly 34 to 54 meters and heights up to about 7 meters according to recent reports. This suggests a surprisingly deep understanding of landscape engineering. Builders had to select ground that would drain well, resist erosion, and remain visible from the Oslofjord. Boré was not hidden in a forest. It was placed where ships moving along the fjord could see the power of the dead. The cemetery worked like a political monument, a warning, and a memory system. Its technology was not only underground, it was also in the placement of the entire landscape. Recent non-invasive archaeology has made Boré even more mysterious. Ground-penetrating radar surveys revealed 3 large structures near the mound cemetery, interpreted as high-status halls. One study describes Boré as a late Iron and Viking Age royal site, with monumental mounds and buildings dating broadly between AD 400 and 1050. These halls suggest that the cemetery was not isolated. It may have been part of a living centre of power, where feasts, rituals, leadership, and burial ceremonies were connected. That changes the meaning of the buried ship. It was not just a grave object. It may have been the central piece in a public performance. Imagine a vessel once built for the sea being hauled inland, watched by hundreds of people filled with elite objects, then slowly erased under earth. The ship's technology became sacred because everyone understood its value. To bury such a vessel was to destroy wealth on purpose. Only a ruler with enormous resources could do that. The Boré style of ornament adds another layer. Objects from the site help define a Viking art style known for animal and knot patterns. These designs were not decoration alone. They marked status, identity, and cultural reach. The same society that could engineer flexible hulls could also produce intricate metalwork. In Boré, shipbuilding, burial architecture, and elite art meet in one place. Still, the greatest unanswered question remains technical. How much of the shipbuilding knowledge can we truly recover when the ship itself is gone? Rivets tell us where planks were joined, but not exactly how the carpenter judged curvature. Soil stains show the hull's ghost, but not the sound of tools, the moisture of the timber, or the sequence of assembly. The archaeological record preserves the result, not the method. Citânia de São Fins was not discovered in a desert or a jungle, but on a granite hill in northern Portugal, in the municipality of Pacos de Ferreira. Archaeologists first studied it in 1895, and major excavations later revealed one of the most important hill-fort cities of the Castro culture. At first glance, it looks like a ruined village of circular stone houses, but from above the site becomes stranger. Citânia de São Fins covers about 15 hectares. Around 180 structures have been uncovered. Its occupation developed between the 5th century before Christ and the Roman period, lasting into the 1st centuries after Christ. This was not a temporary refuge. It was a fortified urban system built on stone, slope, water, and repeated calculation. The first mystery is the city's relationship with the hill itself. Many ancient settlements were placed on high ground for defense, but São Fins seems to have transformed the entire hill into a controlled machine. The builders did not simply occupy the summit. They wrapped it with multiple lines of walls, arranged roads across uneven terrain, grouped houses into neighborhoods, and shaped circulation through gates and passages. Compared with a Roman town, which often followed a formal grid, São Fins feels less geometric, yet it is not chaotic. Its order is hidden inside the landscape. The walls are the most visible proof. Built from local granite, they form several defensive lines, with inner circuits and outer protection on vulnerable sides. Granite is extremely hard, dense, and unforgiving. A cubic meter can weigh about 2.6 to 2.7 tons. Even a modest block could weigh hundreds of kilograms. Yet thousands of stones were quarried, selected, transported, lifted, and locked into place without modern cranes, steel tools, engines, or cement. The question is not whether people could move stone. Ancient societies did this many times. The question is how a hill fort community organized the labor so precisely that the system could expand and survive for centuries. Unlike the pyramids of Egypt, Sanfin's does not impress through giant single blocks. Its mystery lies in repetition. One wall stone is ordinary. 10,000 wall stones become an engineering statement. Every block had to be chosen for weight, shape, position, and stability. In dry stone construction, the smallest mistake spreads pressure through the whole wall. If the inner fill is weak, the face bulges. If drainage is poor, water forces the stones apart. If the foundation is uneven, the wall cracks along the slope. Yet many Castro walls in northern Portugal and Galicia endured for more than 2,000 years, even after abandonment, erosion, farming, and later reuse of stone. This raises a deeper technical question. Did the builders work only by eye, or did they possess a practical surveying system now lost to archaeology? Citania de Sanfin has a main north-south street, smaller east-west roads, domestic clusters, defensive gates, and controlled access points. To build this across a hill, someone had to understand gradients, distances, visibility, and movement. They did not need written blueprints in the modern sense, but they needed a mental blueprint repeated by builders who knew how to turn irregular terrain into a functioning settlement. The houses add another layer. Many were circular, about 5 meters in diameter, built with granite walls and roofs made from perishable materials. Several houses were grouped around shared patios, forming family compounds of roughly 200 to 300 square meters. This is important because it suggests social planning, not random shelter. A household was not just one building, it was a small architectural unit: sleeping space, storage, cooking, work areas, courtyard, boundary wall, and access path. In a city with more than 150 visible structures, this means the builders repeated a standard domestic formula many times while still adapting each unit to the hill. That standardization is one of the strangest signs of hidden knowledge. If circular houses repeatedly appear with similar proportions, then measurement existed in some form. Perhaps they used ropes, wooden rods, body-based units, or simple geometry. A circular house can be laid out with a central stake and cord. But doing this again and again while fitting compounds into roads and walls requires more than a casual method. It requires shared rules. Those rules were never written down, or if they were, they did not survive. The drainage problem may be even more important than the stones. Northern Portugal receives heavy seasonal rain. On a hill fort, rain is an enemy. It runs downhill, cuts paths, weakens foundations, floods courtyards, and pushes against retaining walls. A settlement of this size could not survive if water moved randomly. The builders had to make water visible in their minds before it arrived. Streets needed slope, floors needed elevation, walls needed stable bases, open spaces needed runoff. Compared with Roman aqueducts, this system is less spectacular because there are no towering arches, but technically, hillside drainage can be just as demanding. A failed aqueduct is obvious. A failed drainage system destroys a city slowly from below. The public bath structure, often linked with the so-called Pedra Formosa tradition of Castro culture, makes the problem more mysterious. These bath or sauna-like buildings required controlled heat, stone chambers, water management, and symbolic architecture. At Sanfins, The presence of this bathing tradition suggests that water was not only practical, it may have been social, ritual, and technological at the same time. The builders understood how stone, heat, steam, and enclosed space interacted, yet almost none of the operating instructions survive. Archaeologists can excavate the stones, but not the gestures, how the fire was managed, how water was poured, how temperature was controlled, how many people entered or what rituals surrounded the experience. Then there is the mystery of labour. A city of 15 hectares cannot be built by a few families in spare time. It required quarrying crews, transport routes, food supply, tool production, seasonal planning and leadership. Someone decided where walls would go. Someone maintained roads. Someone coordinated repairs. Someone knew which stones were useful and which would fail. In modern construction, these roles are divided among engineers, foremen, surveyors, masons, and logistics managers. At Sandfins, all those functions existed, but their titles are unknown. The city preserves administration without documents. The comparison with Roman engineering is revealing. Roman towns often used mortar, standard plans, written administration, roads, baths, and formal public buildings. Sandfins emerged from a different tradition. Its knowledge was more local, more oral, and more tied to stone landscapes. When the Roman world expanded into northwestern Iberia, it did not simply erase these hill forts. Some were adapted, reused, or transformed. That means Castro engineering was not primitive debris waiting to be replaced. It was valuable enough to survive contact with Rome. Yet Romanization also complicates the site. Some features belong to earlier Iron Age occupation. Others reflect later change. Roman coins, pottery, and occupation layers show that the settlement did not remain frozen in one cultural moment. This makes Sandfins harder to read. When archaeologists see a wall, a road, a house, or a repaired surface, they must ask whether it belongs to the original Castro system, a later modification, or a Roman period adaptation. The city is not one mystery, it is a layered machine rebuilt over generations.